Over billions of years, matter flowed along the filaments of the cosmic web, pooling at nodes where gravity drew it together. Small groups merged into larger associations, and larger associations into clusters. The clusters we observe today are the product of 13 billion years of cosmic evolution, still growing as galaxies and groups fall inward along the tendrils of the web. The scale of clusters also manifests in time. These structures did not arise overnight, but grew gradually from the small density fluctuations present in the early universe. Even now, clusters are not static but dynamic, continually accreting, colliding and evolving, the largest bound systems still actively under construction. Philosophically, to contemplate the structure and scale of galaxy clusters is to confront our own smallness. Each galaxy within a cluster contains billions of stars, many of them with planets, each planet perhaps with its own histories and mysteries. Multiply that by 1,000 galaxies, and then multiply that by the countless clusters spread across the visible universe, and one begins to sense the immensity of the cosmos. Yet clusters are not just anonymous numbers. They are specific places, structured communities with their own dynamics and histories. Just as cities on Earth have their neighborhoods, their economies, their struggles and triumphs, so do clusters in the universe, bound together in patterns of gravity, shaped by flows of gas, lit by the faint glow of galaxies wandering through their halls. The structure and scale of galaxy clusters make them keystones in cosmology. They are the largest gravitationally bound structures in existence, the nodes of the cosmic web, the bridges between galaxies and the universe itself. They reveal dark matter in their mass, hot gas in their glow, and the dynamics of structure formation in their growth. They are both the cities of galaxies and the cities of the universe, where the great processes of cosmic architecture are most clearly written. In their immensity and order, they remind us that the cosmos is not chaos but structure, not void but hierarchy. A place where gravity has built cathedrals of galaxies across the canvas of space-time. The grandeur of galaxy clusters lies not only in the sheer number of galaxies they contain, but in the invisible forces and hidden matter that bind them together. If one were to look only at the starlight of their constituent galaxies, the picture would be woefully incomplete. The visible stars, scattered across thousands of galaxies, represent only a small fraction of the total mass of a cluster. What truly holds these cosmic metropolises together is the overwhelming gravity of unseen dark matter and the seething weight of hot gas that permeates their interiors. In many ways, the galaxies themselves are like bright street lamps in a city, giving shape to the night but not reflecting the true foundation upon which everything rests. The streets, buildings, and invisible infrastructure of the cosmic city are provided by gravity and gas, the two elements that dominate the life of clusters. Gravitational binding is the unifying principle of clusters, the silent force that brings coherence to what would otherwise be chaos. Without it, the galaxies within a cluster would simply fly apart, flung outward by their own orbital velocities. Measurements of those velocities were among the first hints that something unseen was at work. In the 1930s, Fritz Zwicky studied the Coma cluster and realized that the galaxies within it were moving far too fast to be held together by the gravity of visible matter alone. He coined the term dunkle Materie, dark matter, to explain the missing mass, introducing a concept that would grow into one of the central mysteries of modern cosmology. His observation has been confirmed countless times since. In every cluster, the galaxies are simply moving too quickly for their visible stars to provide sufficient binding. The invisible outweighs the luminous. The shadow outweighs the light. This dark matter halo envelops the entire cluster, stretching far beyond the visible galaxies. It is not a thin layer, but a vast, diffuse scaffold, hundreds of times more massive than all the stars combined. Simulations of structure formation show that these halos are the gravitational wells into which gas falls, forming galaxies as byproducts of deeper, unseen structures. The galaxies we see in clusters are like leaves floating on a river, carried by currents of dark matter that shape their motions and destinies. The halo provides the skeleton, while the galaxies are merely ornaments on the bones of gravity. Within this dark framework lies another vital component: the hot intracluster medium. This plasma, heated to tens of millions of degrees, fills the spaces between galaxies and is observable in X-rays. Far from empty voids, the interiors of clusters are suffused with this glowing gas, whose mass often exceeds that of the galaxies themselves. In clusters like Perseus or Coma, the X-ray emission is so intense that it rivals the brightness of the galaxies in other wavelengths. The intracluster medium is both a record and an actor. It records the history of mergers and collisions in its shock waves and ripples, and it acts to shape the lives of galaxies by stripping their gas and quenching their star formation. The physics of this hot gas is complex. It is not static, but constantly stirred by motion, collisions, and feedback from supermassive black holes at galactic centers. As subclusters merge into larger ones, the gas is shocked and heated, sometimes creating long tails and filaments visible in X-ray images. Jets from central black holes inflate cavities in the plasma, displacing the gas and heating it further. Cooling flows, once thought to condense into new stars at rapid rates, are now known to be counterbalanced by heating from these same jets. The result is a delicate equilibrium, where the gas neither cools too quickly nor overheats, a balance maintained by the interplay of gravity, plasma physics, and black hole feedback. The presence of the intracluster medium also transforms the galaxies that fall into clusters. Spirals that once thrived in the field, with arms rich in star-forming gas, are stripped bare as they plunge through the hot plasma. Their cold gas is blown away by ram pressure, leaving behind smooth, gas-poor galaxies unable to form new stars. This is why clusters are dominated by ellipticals and lenticulars, galaxies that have been quenched of star formation by their environments. The hot gas acts as a sterilizing field, burning away the raw material for stellar birth and enforcing a kind of galactic conformity. In this way, clusters are engines of transformation, reshaping galaxies as they assimilate them into their crowded halls. Philosophically, the gravitational binding and hot gas of clusters represent the hidden forces that shape reality. The stars are visible, bright, and immediate, but they are secondary to the unseen and the intangible. The dark matter halo cannot be seen but outweighs everything else. The hot plasma does not shine in visible light, but dominates the mass budget of baryonic matter. What we see in optical telescopes is only the frosting on a cake, whose substance lies in shadows and heat. To understand clusters is to accept that the universe is structured not by the obvious, but by the hidden, not by the luminous, but by the invisible. These discoveries also provide crucial evidence for cosmology. The relative amounts of galaxies, gas, and dark matter in clusters help constrain the composition of the universe itself. By measuring the baryon fraction, the ratio of normal matter to total mass, astronomers test cosmological models and verify that dark matter and dark energy dominate the cosmic inventory. Clusters thus serve as weighing scales for the universe, their gravity and gas, revealing the proportions of matter and energy that shape cosmic history. Looking ahead, the study of gravitational binding and hot gas in clusters will continue to illuminate mysteries at the frontier of astrophysics. Instruments like the ERO, SITA X-ray telescope and the upcoming Athena mission will map the hot gas in unprecedented detail, revealing the thermodynamics of the intracluster medium and the interplay of cooling and heating. Gravitational lensing studies, which trace the bending of light by dark matter halos, will refine our maps of the invisible scaffolding. Together, these approaches will deepen our understanding of how clusters hold together, how they evolve, and how they encode the story of cosmic matter itself. In the end, the gravitational binding and hot gas of galaxy clusters remind us that what is essential is often hidden. Stars, galaxies, and light are only the surface. Beneath them lie vast reservoirs of invisible mass and unseen plasma, the real foundations of the largest structures in the universe. Clusters are not cities of galaxies alone, but cities of dark matter and gas, where the luminous plays only a minor role. To study them is to look beyond appearances, to weigh the unseen, and to glimpse the architecture of the cosmos in its truest form. Among the many galaxy clusters scattered across the cosmos, few have had as profound an impact on our understanding of the universe as the Bullet cluster. At first glance, it appears to be just another merging pair of galaxy clusters, two cosmic cities colliding in a slow-motion crash that has unfolded over hundreds of millions of years. But when astronomers studied this system in detail, they uncovered some of the most striking evidence for the existence of dark matter, transforming the Bullet cluster into a cornerstone of modern cosmology. It is not merely an astronomical curiosity, but a kind of cosmic experiment, where nature has staged a collision large enough to reveal what is normally invisible. The Bullet cluster, formerly known as 1E0657-56, lies about 3.8 billion light-years away in the constellation Carina. What we see today is the aftermath of two clusters that pass through one another at incredible speed, their galaxies streaming past with little direct interaction. Galaxies are so sparsely distributed that even in a collision of clusters, individual galaxies rarely collide. Instead, the drama plays out in the gas and in the gravity. The intracluster gas, which makes up most of the normal matter, slam together in a violent shock front, producing a bright, bullet-shaped feature visible in X-ray images. This bow shock, the fastest ever observed in such a system, gives the cluster its evocative name. The galaxies, meanwhile, passed largely unscathed, continuing their orbits as if nothing had happened. But what truly made the Bullet cluster extraordinary was the way these different components separated during the collision. By combining X-ray observations of the hot gas with gravitational lensing maps of the cluster's mass, astronomers saw something astonishing. The gas, which contains most of the normal baryonic matter, was slowed and displaced by the collision, bunching up in the center. But the gravitational lensing signal, the bending of background light by the cluster's total mass, did not align with the gas. Instead, the mass was concentrated around the galaxies, which had sailed through the collision without much resistance. In other words, most of the mass in the cluster did not follow the visible matter, but remained aligned with the dark halos surrounding the galaxies. This separation of mass from baryons was the smoking gun, direct visual evidence that most of the matter in the universe is invisible and does not interact with normal matter except through gravity. For decades, the existence of dark matter had been inferred from indirect clues: the rotation curves of galaxies, the velocities of galaxies within clusters, the structure of the cosmic web. These were persuasive but circumstantial. The Bullet cluster provided something more tangible, a cosmic laboratory where the behavior of matter and mass could be observed in action. The hot gas behaved like normal matter should, colliding, heating, and slowing. The dark matter halos, by contrast, slipped through like ghosts, unaffected except by gravity. Their presence was revealed not by their light, but by their effect on background galaxies, whose shapes were distorted into arcs and shears by the invisible mass. No alternative explanation has yet matched this observation as convincingly as the existence of dark matter. the bullet cluster also provided constraints on the properties of dark matter. Because the dark halos pass through each other with little interaction, the collision placed limits on how strongly dark matter can scatter or self-interact. If dark matter particles collided with one another the way baryons do, the mass distribution would have lagged or smeared out. Instead, the halos remained intact, suggesting that dark matter interacts only weakly, if at all, beyond gravity. This has ruled out some models of exotic physics and narrowed the field of candidates, even as the true nature of dark matter remains unknown. Other merging clusters have since been studied, such as the Musket Ball cluster and El Gordo. And they too show separations between gas and mass, consistent with dark matter. But the bullet cluster remains the most iconic, both for the clarity of its features and for its dramatic bow shock, a visible arrowhead pointing to the hidden truth of the universe. It is often shown as the definitive photograph of dark matter, the closest thing to an image of the invisible that science has yet produced. Philosophically, the bullet cluster carries weight beyond astrophysics. It demonstrates how the universe itself can conduct experiments far beyond our means, setting up collisions so vast that they reveal the properties of matter on the grandest scales. No laboratory on Earth could reproduce such conditions, yet by observing carefully, we are able to extract truths about the fundamental components of reality. The bullet cluster also reminds us that the visible universe is not the true universe. The light we see, the gas we map, is only a minority component. The true mass, the true architecture, lies hidden in shadows, detectable only by its gravitational hand. This revelation has implications for how we think about our place in the cosmos. Humanity has always been drawn to the luminous, stars, galaxies, quasars, and nebulae, as the visible expressions of cosmic order. But the bullet cluster teaches that light is only a tracer of something deeper, that the scaffolding of the universe is built not of brilliance, but of darkness. To understand the cosmos, we must look not only at what shines, but also at what bends, distorts, and holds together. Looking forward, observations of more cluster collisions will refine these lessons. Surveys with gravitational lensing and X-ray telescopes will map dozens of merging clusters, comparing their mass and baryon distributions. Instruments like the James Webb Space Telescope and the Vera Rubin Observatory will add background galaxies to lensing analyses, sharpening mass reconstructions. In the coming decades, these cosmic laboratories may constrain dark matter properties more tightly than particle colliders on Earth. Each collision, each bow shock, each separation of light from gravity will be another step toward unraveling the invisible. In the end, the bullet cluster remains one of the most eloquent arguments for dark matter, a cosmic tableau where the invisible reveals itself through its contrast with the visible. It is a reminder that truth in science often lies in contradictions. The galaxies sail through while the gas slams to a halt. The light gathers in one place while the mass gathers in another. From these contradictions emerges clarity, the unmistakable conclusion that the universe is built on foundations we cannot see. The bullet cluster is thus both a place and a parable, a place where galaxies collided long ago, and a parable of how the universe hides its secrets in plain sight, waiting for us to look with the right eyes. Galaxy clusters are not only massive cities of galaxies bound by gravity, they are also among the most important tools for understanding the large-scale structure of the universe. Their immense scale and abundance make them cosmic signposts, markers of the invisible web that stretches across billions of light years. By studying where clusters lie, how they evolve, and how their masses shape the light around them, astronomers can use clusters as natural measuring rods, compasses, and laboratories to map the universe itself. They are both objects of wonder and instruments of science, serving as the scaffolding on which cosmology rests. The first way clusters map the cosmos is through their distribution in space. Clusters are not scattered randomly, but follow the same filaments of the cosmic web that trace dark matter across the universe. Their clustering patterns, when measured across millions of light years, encode the underlying geometry and composition of the cosmos. By surveying thousands of clusters, astronomers reconstruct the skeleton of the universe, revealing the vast filaments and voids that define its shape. The Sloan Digital Sky Survey and other wide-field projects have shown that clusters align along cosmic highways of dark matter, confirming that the universe's structure is not chaotic but patterned, the legacy of primordial fluctuations amplified by gravity. Each cluster is thus a node in the grand design, a lighted intersection in the web of matter stretching from the Big Bang to today. Another way clusters serve as cosmic maps is through gravitational lensing. Because clusters are so massive, their gravity bends and magnifies the light of background galaxies, distorting them into arcs, streaks, and multiple images. These natural lenses reveal galaxies far too distant or faint to be seen otherwise, allowing us to peer deeper into the early universe. Some of the most distant galaxies known have been glimpsed only because their light passed through a cluster lens on its way to Earth. The Hubble Frontier Fields program, for example, used clusters as magnifying glasses to uncover galaxies that formed less than 1 billion years after the Big Bang. In this way, clusters not only reveal themselves, but also serve as windows to epochs otherwise beyond our reach. Their gravitational wells become telescopes writ large, instruments of nature that extend the reach of our machines. Lensing also allows astronomers to map the distribution of dark matter within clusters. By analyzing the distortions of background galaxies, scientists reconstruct the invisible halos that hold clusters together. These maps reveal the clumpiness of dark matter, its concentration near cluster cores, and its extension into diffuse halos. In merging clusters like the Bullet cluster, lensing has provided some of the clearest evidence that dark matter is real and distinct from baryonic matter. But even in ordinary clusters, lensing paints a picture of the hidden scaffolding of the cosmos, showing how gravity shapes matter on the largest scales. Each distorted galaxy in the background is a clue, each arc a data point, together building a map of the unseen skeleton of reality. Clusters are also vital in tracing the expansion of the universe. Their abundance and growth rate over cosmic time depend sensitively on cosmological parameters, like the matter density and the strength of dark energy. By counting how many clusters exist at different epochs, astronomers can test theories of cosmic acceleration. This method, known as cluster cosmology, treats clusters as statistical markers, their very numbers encoding the properties of space-time. Observations with X-ray telescopes, Sunyaev-Zeldovich surveys of the cosmic microwave background, and optical surveys of galaxy populations all contribute to this cosmic census. The more clusters we count and weigh, the more precisely we measure the parameters that define our universe. In this sense, clusters are like mile markers on the road of cosmic expansion, signposts telling us how far and how fast we have traveled since the beginning of time. Another crucial role comes from the hot intracluster medium, which interacts with the cosmic microwave background through the Sunyaev-Zeldovich effect. As photons from the relic radiation of the Big Bang pass through the plasma of a cluster, they gain a slight energy boost, leaving subtle imprints in the background sky. By mapping these distortions across the sky, astronomers can detect clusters independently of their light and measure their properties with extraordinary precision. This method provides a nearly redshift-independent way to find clusters across billions of light years, making them powerful probes of cosmic history. Through the Sunyaev-Zeldovich effect, clusters not only map themselves, but also provide insight into the earliest light of the universe, linking the end of cosmic infancy with the present-day architecture of structure. Clusters also reveal themselves through their role in the cosmic baryon budget. By weighing the ratio of hot gas to dark matter, astronomers can compare the observed fractions with those predicted by cosmological theory. Remarkably, the baryon fraction in clusters matches the ratio derived from the cosmic microwave background, confirming that clusters are fair samples of the universe's matter content. This makes them reliable laboratories for measuring cosmological constants, their mass compositions reflecting the universal recipe of normal and dark matter. Each cluster is therefore a microcosm, a representative slice of the universe, whose contents mirror the larger whole. Philosophically, using galaxy clusters as maps reminds us of the dual nature of science. The objects we study for their own beauty and strangeness also become tools for deeper understanding. Clusters are both cathedrals of galaxies and instruments of cosmology. They are ends in themselves and means to an end, places of grandeur and devices of measurement. In their light and their gravity, we see not only what they are, but what the universe itself is. They remind us that nature often provides its own instruments, its own experiments, if only we know how to read them. Looking ahead, the mapping role of clusters will expand with new surveys. The Vera C. Rubin Observatory will chart thousands of clusters with unparalleled depth, tracing their distribution across cosmic filaments. The Euclid mission and Nancy Grace Roman Space Telescope will use lensing and infrared imaging to measure dark matter in clusters with exquisite precision. Next-generation CMB experiments will refine Sunyaev-Zeldovich maps, detecting clusters across most of cosmic history. Together, these tools will turn clusters into some of the most precise instruments for probing dark energy, testing gravity, and understanding the structure of space-time. In the end, galaxy clusters are not just cities of galaxies, but also maps of the universe itself. They trace the cosmic web, magnify the earliest galaxies, constrain cosmological parameters, and reveal the hidden scaffolding of dark matter. They are markers of space and time, laboratories of physics and cosmology, signposts on the journey from the Big Bang to today. To study them is to see both the particular and the universal, both the beauty of clustered galaxies and the architecture of the entire cosmos. In their immense scale and hidden depths, they reveal not only where the galaxies are, but also how the universe itself has grown, stretched, and evolved. If galaxy clusters are the great cities of the universe, then their mergers are cosmic collisions of empires, vast and violent encounters where titanic structures crash together in slow-motion ballets lasting billions of years. These are among the most energetic events since the Big Bang itself, releasing more energy than supernovae, gamma-ray bursts, and quasars combined. When two clusters merge, galaxies pass largely unharmed, but the seas of hot gas within them slam into one another. Shock fronts ripple across millions of light-years, and the invisible halos of dark matter interpenetrate like colliding shadows. To witness such an event is to glimpse the forces that shape the universe at its grandest scales, where gravity orchestrates the union of the largest bound systems ever to exist. Mergers begin as clusters approach along filaments of the cosmic web, drawn together by their mutual gravity. Over hundreds of millions of years, the two structures accelerate toward one another, their galaxies swirling like dancers, preparing to meet. The first close passage is dramatic. The galaxies glide through mostly unaffected, but the diffuse plasma between them collides head-on, heating to even higher temperatures and generating enormous shock waves. These shocks are visible in X-rays, where astronomers detect bow-shaped fronts reminiscent of sonic booms, evidence of gas slamming together at thousands of kilometers per second. The intracluster medium, already among the hottest and most energetic substances in the universe, is whipped into turbulence, stirred like cosmic soup by the violence of the collision. The galaxies themselves, despite being the most visible constituents of a cluster, are almost bystanders in this drama. The distances between stars are so vast that direct collisions are exceedingly rare. Instead, galaxies continue their orbits, subtly tugged and reshaped by tidal forces, but mostly intact. The true action is invisible. The dark matter halos of the clusters sliding through one another, unaffected except by gravity, merging over time into a single, larger halo. These halos provide the gravitational foundation for the new cluster, which eventually settles into equilibrium after billions of years. In this way, mergers are the engines of cosmic growth, the mechanism by which small groups combine into larger clusters, and larger clusters into superclusters, building the hierarchical structure of the universe. One of the most famous examples of a cluster merger is the bullet cluster, already discussed for its role in providing evidence of dark matter. But it is only one of many. Clusters like El Gordo, a gargantuan merger in the southern sky, display spectacular arcs of gravitational lensing and extreme X-ray luminosities, evidence of the power unleashed when two cosmic giants collide. Others, like the Perseus cluster, show ripples and cavities in their hot gas, not only from mergers, but also from the ongoing interplay with central black holes. Each system is unique, shaped by the masses of the colliding clusters, the angles of their approach, and the stages of their interaction. Some are caught in the act of first collision, others in later stages where the components are still disentangling. Together they form a gallery of cosmic violence, snapshots of a universal process that has been ongoing for billions of years. The physics of these mergers is staggering. Shock waves propagate across distances of millions of light years, compressing and heating gas to temperatures of tens of millions of degrees. These shocks accelerate particles to relativistic speeds, creating vast radio relics, diffuse arc-like sources of radio emission at the peripheries of merging clusters. These relics are the footprints of cosmic accelerators, colossal versions of the processes that occur in supernova remnants. Meanwhile, turbulence stirs the intracluster medium, redistributing energy and mixing metals produced by ancient stars. Galaxies falling into the melee are stripped of their gas, their star formation quenched, their morphologies transformed. Mergers are not just collisions of structures, but crucibles of evolution, reshaping the galaxies within them and enriching the environment with energy and heavy elements. Mergers also play a crucial role in cosmology. Because the rate at which clusters merge depends on the growth of cosmic structure, studying mergers provides insight into dark matter and dark energy. The velocities of colliding clusters, the separations of their mass and gas, the properties of their shock fronts, all serve as tests of cosmological models. For example, El Gordo's extreme mass and high-velocity collision challenge some versions of structure formation, raising questions about whether such a massive merger should have occurred so early in cosmic history. The bullet cluster, as discussed, demonstrates that dark matter behaves differently from baryonic matter, strengthening the case for its existence. In this way, mergers are not only dramatic spectacles, but also laboratories, where the deepest mysteries of the universe can be tested. Philosophically, cluster mergers embody the paradox of creation through destruction. They are violent, unleashing energies beyond imagination. Yet they are also constructive, building larger, more massive structures that persist for billions of years. Out of collision comes coherence. Out of turmoil comes new equilibrium. The shock waves and turbulence that seem chaotic are, in the long view, part of the process by which the universe organizes itself into ever larger systems. Clusters merge not in spite of chaos but because of it, harnessing the violence of collision to fuel the growth of structure. They remind us that destruction and creation are often two faces of the same process, inseparable in the grand cycles of cosmic evolution. From the human perspective, the timescales of mergers are almost incomprehensible. What we capture in images are frozen moments in processes that last billions of years. A merger we observe today may still be unfolding long after humanity is gone. Its final equilibrium achieved only after the Earth has been consumed by the dying sun. In this sense, cluster mergers are slow-motion epics, stories written in spans of time that dwarf all of human history. They invite us to expand our imagination, to think not in years or centuries, but in cosmic ages, where change is measured in the drift of galaxies and the flow of gas across intergalactic voids. Looking forward, the study of cluster mergers is poised for a golden age. Instruments like the Square Kilometre Array will detect the faint radio relics and halos produced by shocks and turbulence, mapping the particle acceleration processes in exquisite detail. Next-generation X-ray observatories, such as Athena, will probe the hot gas with unprecedented resolution, tracing shock fronts, ripples, and turbulence. Gravitational lensing studies will map the dark matter in merging systems, showing how the invisible scaffolding behaves during collisions. Together, these observations will turn cluster mergers into precision tests of cosmology, as well as vivid portraits of the drama of structure formation. In the end, mergers of galaxy clusters are among the universe's grandest spectacles, collisions of giants that both reveal and shape the cosmic order. They are violent yet creative, chaotic yet purposeful, destructive yet constructive. In their shock fronts and bow waves, we see the energy of the cosmos unleashed. In their eventual equilibrium, we see the stability of new structures born. They are both laboratories for understanding dark matter and dark energy, and metaphors for the universe itself, where growth comes not through peace, but through struggle, not through stasis, but through motion. To contemplate them is to confront the immensity of cosmic time and the paradoxes of creation, to see in the merging of galaxies and gas the handwriting of gravity on the largest canvas imaginable. The largest structures in the universe. On the grandest scales, the universe reveals itself not as a random scattering of galaxies, but as a vast and intricate tapestry known as the cosmic web. Stretching across billions of light years, this web is composed of long filaments of galaxies and dark matter, woven together into sheets and nodes, with immense empty regions, cosmic voids, in between. To glimpse the web is to see the architecture of the cosmos itself, the hidden framework upon which all galaxies, clusters, and stars are hung like jewels on an invisible lattice. It is the largest pattern in existence, a structure so immense that even our richest galaxy clusters are mere dots upon its threads. Cosmic filaments are the great highways of matter. They are elongated structures, tens to hundreds of millions of light years in length, filled with galaxies, clusters, and diffuse gas, all bound by the gravity of dark matter halos. Galaxies are not distributed evenly across the universe, but flow along these filaments like traffic along interstellar superhighways, converging at the dense nodes where clusters of galaxies form. In this way, filaments are both channels and scaffolds, guiding matter toward the intersections where the largest bound structures emerge. Simulations of cosmic evolution show that filaments grew from the tiny ripples in density that existed in the early universe, seeded by quantum fluctuations and amplified by gravity over billions of years. What began as minuscule variations in the cosmic microwave background became rivers of galaxies spanning hundreds of millions of light years. Between these filaments lie the cosmic voids, vast, almost empty expanses that can stretch across hundreds of millions of light years. Voids contain very few galaxies, sometimes only a handful across their immense volumes. They are the dark, empty halls between the luminous filaments, the negative spaces that define the shape of the web. Though empty compared to filaments, voids are not entirely barren. They contain faint wisps of dark matter and thin gases, the traces of structure too rarefied to ignite into galaxies. To imagine standing within such a void, if such a thing were possible, would be to see galaxies concentrated on the horizon in faint arcs, with the rest of the sky nearly black, a cosmic desert with civilization only on its distant edges. The scale of this structure dwarfs human comprehension. The local group, containing the Milky Way and Andromeda, lies within a filament that is itself part of a larger structure known as the Laniakea supercluster, spanning over 500 million light-years. And yet even this is just one strand in a far larger web that stretches across the visible universe. Each filament connects to others, creating a mesh of matter that resembles neural networks or the delicate strands of a spider's web. The resemblance is not superficial. The mathematics of filamentary networks applies to both, suggesting that the universe may be governed by patterns of connectivity that appear across scales, from the microscopic to the cosmic. Observationally, the cosmic web has been revealed gradually. The first hints came from redshift surveys in the late 20th century, which measured the positions of thousands of galaxies and mapped their three-dimensional distribution. Rather than appearing random, galaxies formed walls, arcs, and threads, leaving yawning voids in between. The CFA redshift survey was among the first to reveal this, showing slices of the universe in which galaxies traced out great structures that looked like bubbles in foam. Subsequent surveys, like the Sloan Digital Sky Survey, SDSS, expanded this picture, cataloguing millions of galaxies and confirming that the cosmic web is the fundamental large-scale structure of the universe. The formation of filaments and voids is intimately tied to dark matter. Ordinary matter alone would not have been able to form such vast structures. It is the gravitational pull of dark matter, outweighing visible matter by a factor of 5, that created the filaments. As the universe expanded, dark matter clumped into halos, and baryonic gas followed, cooling into stars and galaxies along the densest threads. Voids, by contrast, are the natural consequence of this growth. Regions that began slightly underdense expanded faster than their surroundings, evacuating material into the filaments and leaving behind vast, underpopulated expanses. The universe, in other words, amplified its initial wrinkles into a grand pattern of walls and gaps, a cosmic architecture written in light and shadow. Philosophically, the cosmic web and its voids embody the duality of fullness and emptiness. The filaments are crowded with galaxies, the nodes with clusters and superclusters, the centers of activity and creation. The voids are silent, vast, and empty, places where galaxies never gathered. Yet both are essential. Without the voids, the filaments would not stand out. Without the emptiness, the fullness would have no meaning. The web is a balance of density and absence, of threads and gaps, a structure where creation and silence coexist. To contemplate the web is to glimpse how the universe itself is sculpted by contrasts, how its beauty emerges from the interplay of what is present and what is missing. The cosmic web also serves as a natural map of cosmic history. By studying the distribution of filaments and voids at different redshifts, astronomers trace how structure has grown over time, testing models of dark energy and cosmic expansion. The shapes of filaments, the sizes of voids, the clustering of nodes, all encode information about the laws that govern spacetime. If dark energy accelerates expansion, voids should grow larger more quickly. If dark matter has unexpected properties, the filaments may be thicker or thinner than predicted. In this way, the very geometry of the cosmic web becomes a test of fundamental physics, a silent but eloquent record of the forces that shape the universe. Looking forward, new surveys and simulations will sharpen our view of the web. Instruments like the Vera C. Rubin Observatory and the Euclid mission will map galaxies deeper and farther than ever before, filling in the threads of the web with exquisite detail. Cosmic microwave background experiments will trace the imprints of filaments on ancient radiation, revealing how they grew from the earliest times. Computer simulations, meanwhile, will continue to refine our understanding, showing how galaxies, gas, and dark matter coalesce into the intricate patterns we observe. Together, they will transform the web from a suggestive sketch into a detailed blueprint of the universe's architecture. In the end, cosmic filaments and voids are the stage upon which all other cosmic dramas unfold. Galaxies, clusters, and quasars are but players upon the threads, their light revealing the outlines of an invisible structure that stretches across space and time. To see the web is to recognize that the universe is not random, but patterned, not uniform, but woven. Its filaments are the highways of galaxies, its voids the empty fields between, together forming the largest structure ever observed. In this grand architecture, we glimpse both the immensity of the cosmos and the subtlety of its design, a universe shaped not only by what it contains, but by the spaces in between. Among the filaments and superclusters that form the scaffolding of the cosmic web, one structure captured particular attention at the dawn of the 21st century: the Sloan Great Wall. When it was first revealed in 2003 through the Sloan Digital Sky Survey, SDSS, it instantly became one of the largest known coherent features in the universe, a sprawling concentration of galaxies stretching across more than 1 billion light-years. Its discovery was both awe-inspiring and unsettling, because it seemed to push the limits of what cosmologists thought possible for large-scale structures to grow under the rules of cosmic expansion and gravitational clustering. The Sloan Great Wall is not a single galaxy cluster or supercluster, but rather a vast chain of clusters, filaments, and sheets woven together into one of the universe's grandest walls of matter. To understand the significance of the Sloan Great Wall, one must recall the scale involved. The Milky Way is roughly 100,000 light-years across. The local group, our galactic neighborhood, spans a few million light-years. The Virgo supercluster, of which we are a part, extends about 100 million light-years. The Sloan Great Wall, by comparison, stretches across some 1.4 billion light-years of space. In terms of sheer scale, it is over 10,000 times longer than the Milky Way, a structure so vast that it rivals the observable reach of some of the earliest galaxy surveys. If one could view the universe from afar, the Sloan Great Wall would appear as a glowing band, an immense ridge of galaxies stitched together into a wall-like formation. The wall is not a continuous sheet of stars, but a collection of galaxy clusters and filaments bound into a common structure. Like bricks in a wall, each galaxy cluster is a component, held together by the larger framework of dark matter. Some parts are densely packed nodes where galaxies swarm in rich abundance, while others are elongated filaments bridging the gaps, tracing out invisible rivers of mass. Between these bright ridges lie vast voids, empty stretches where galaxies are scarce, making the Sloan Great Wall appear even more striking by contrast. This alternation of density and emptiness, of wall and void, is characteristic of the cosmic web. But the Sloan Great Wall magnifies it to an unprecedented degree. The discovery was made possible by the Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken. By measuring the redshifts of hundreds of thousands of galaxies, the SDSS provided a three-dimensional map of the universe on scales never before achieved. When the data was plotted, astronomers saw the Sloan Great Wall emerge, a sweeping ridge of galaxies too coherent and too large to ignore. It quickly became a touchstone in discussions about the larger structures, surpassing earlier discoveries like the CFA-2 Great Wall, found in the 1980s. Each new map of the cosmos seemed to reveal an even larger structure, raising questions about whether there is any true upper limit to cosmic size. The Sloan Great Wall also presented a challenge to cosmological theory. According to the cosmological principle, the universe on the largest scales should be homogeneous and isotropic, meaning that matter should appear evenly distributed when averaged over sufficiently vast distances. The existence of structures as large as the Sloan Great Wall seemed to test the boundaries of this principle. Could such a structure arise naturally within the standard model of cosmology? Or did it represent a statistical anomaly, a chance alignment of filaments that only looked coherent from our perspective? Computer simulations based on the lambda cold dark matter model suggest that structures of this size are improbable, but not impossible, lying near the upper edge of what might occur by chance. Yet its sheer presence continues to provoke debate, a reminder that the universe often surprises us with its scale and complexity. The Sloan Great Wall is also significant for what it reveals about the growth of structure over time. By studying the galaxies within it, astronomers can trace how matter assembled from the early universe to the present. The galaxies in the wall show signs of having evolved differently from isolated galaxies, influenced by their dense environments. Star formation rates are suppressed in many regions, as galaxies within rich clusters consume their gas quickly or lose it through interactions. In this sense, the wall is not just a structure of matter, but also a structure of history, a record of how environment shapes the fate of galaxies across billions of years. Philosophically, the Sloan Great Wall forces us to think about boundaries. When does a collection of filaments and clusters become one structure? And when is it merely a chance alignment? How do we define coherence across distances so large that light itself takes over 1 billion years to cross them? These are not just scientific questions, but conceptual ones, probing the limits of how humans categorize the universe. The term wall reflects our attempt to describe the indescribable, to impose metaphors of human architecture upon scales that dwarf imagination. Yet the metaphor works. The Sloan Great Wall is indeed a wall, a ridge of galaxies stacked and aligned, rising from the cosmic void like a fortress of light. In a broader sense, the wall exemplifies the tension between order and chaos in the universe. The Big Bang gave rise to a nearly uniform sea of matter and radiation, punctuated only by slight ripples in density. Over billions of years, gravity amplified those ripples into galaxies, clusters, and filaments. The Sloan Great Wall is a pinnacle of that process, a monument to the ability of gravity to organize chaos into structure. Yet, its very size hints at randomness, at the improbability of such a vast and coherent feature arising by chance. It sits at the intersection of necessity and accident, a cosmic structure that may be both an inevitable outcome of physics and a statistical outlier in the role of cosmic dice. Looking ahead, the Sloan Great Wall will continue to be a benchmark for cosmology. Future surveys, mapping millions more galaxies across larger volumes of space, may uncover even greater structures, perhaps dwarfing even this wall. Or perhaps the Sloan Great Wall will stand as one of the largest coherent features possible, a natural ceiling on the scale of cosmic architecture. Either way, it has already transformed our understanding of the universe's structure, showing us that even across billions of light years, galaxies are not sprinkled randomly, but arranged into vast, interconnected patterns. In the end, the Sloan Great Wall is more than a scientific discovery. It is a reminder of the grandeur of the cosmos. It is a testament to the power of human observation, to our ability to map and measure structures so large that their very existence challenges the boundaries of our theories. It is also a monument to gravity, the simple yet relentless force that sculpts matter into walls, filaments, and clusters. To contemplate the Sloan Great Wall is to confront immensity, to recognize that the universe is not only larger than we imagine, but structured in ways that seem almost beyond imagination. If the Sloan Great Wall astonished astronomers with its billion-light-year sprawl, then the discovery of the Hercules-Corona Borealis Great Wall left them nearly speechless. Announced in 2013, this colossal structure, stretching across 10 billion light-years of space, is by some measures the largest single entity ever identified in the observable universe. It dwarfs not only the Milky Way or even the local supercluster, but also entire walls of galaxies like the Sloan Great Wall. It is so immense that light itself, traveling at cosmic speed, would take about 10 billion years to traverse its length, nearly 3/4 of the age of the universe. The Hercules-Corona Borealis Great Wall is not simply a structure. It is a staggering reminder that the universe is capable of assembling features on scales that strain our theories, our expectations, and even our imagination. Unlike the Sloan Great Wall, which was mapped through galaxy redshift surveys, the Hercules-Corona Borealis Great Wall was discovered in a different way, through the distribution of gamma-ray bursts GRBS. These violent explosions, the brightest events in the cosmos, occur when massive stars collapse or when neutron stars merge, releasing torrents of gamma radiation visible across billions of light-years. Because GRBS are tied to the deaths of stars, they serve as tracers of galaxy locations at great distances. When astronomers analyzed the distribution of hundreds of GRBS, they noticed an unusual clustering of events across a swath of the sky, stretching from the constellations Hercules and Corona Borealis. Instead of being randomly scattered, the bursts aligned into a pattern suggesting an underlying structure of galaxies on a scale never before seen. The implication was staggering: an interconnected web of galaxies spanning 10 billion light-years. If true, this structure challenges not just the limits of known superclusters, but the very foundations of cosmology. According to the cosmological principle, the universe should appear homogeneous and isotropic on the largest scales. That is, when averaged over hundreds of millions of light-years, the universe should smooth out, without features of such overwhelming size. The Hercules-Corona Borealis Great Wall appears to defy this principle, existing as a coherent feature so vast that it stretches the definition of large-scale structure almost beyond recognition. Some astronomers have argued that it may not be a single continuous object, but a statistical alignment of several smaller walls and filaments. Yet even if that is the case, the fact that the alignment appears across such enormous distances remains a profound puzzle. The discovery sparked immediate debate. Could the clustering of gamma-ray bursts simply be a coincidence, the result of small sample sizes and observational bias? Or was it evidence of a genuine superstructure, unlike anything predicted? Subsequent analyses have leaned toward the latter, suggesting that while some randomness is involved, the likelihood of such a clustering happening by chance is low. More GRBs have since been observed in the same region, reinforcing the suspicion that we are indeed looking at a real, coherent feature of cosmic architecture. But because the structure is so distant and so large, it remains difficult to study directly through galaxy redshift surveys, leaving much about its true nature shrouded in uncertainty. If the Hercules-Corona Borealis Great Wall is genuine, it raises profound questions. How could such a structure form in only a few billion years after the Big Bang? Standard cosmological simulations, which use cold dark matter and dark energy to model structure formation, predict large filaments and superclusters, but not features on this scale. To assemble a wall spanning 10 billion light-years requires coherence across a region larger than theory comfortably allows. Does this mean our understanding of dark matter is incomplete, or that the initial conditions of the universe were more irregular than we thought? Or is this structure a statistical fluke in an otherwise smooth cosmos, an outlier rather than a rule? These questions remain open, and each new observation either deepens the enigma or challenges our preconceptions. The Hercules-Corona Borealis Great Wall also has philosophical implications. It forces us to ask whether there are limits to the universe's architecture, whether there is a maximum scale beyond which structure dissolves into randomness. For decades, cosmologists assumed that scale was on the order of 1.2 billion light-years, the end of greatness, beyond which homogeneity prevailed. The Hercules-Corona Borealis Great Wall defies that limit, suggesting that the universe may be capable of organizing itself into patterns far larger than expected. If so, then our very assumptions about cosmological principles may require revision. What we once thought of as a smooth background may be textured with features so immense that they redefine our sense of cosmic order. Visually, one must imagine this wall not as a solid object, but as a vast collection of galaxies, filaments, and clusters spread across an immense swath of space. From within, it would not appear as a wall at all, but as the horizon filled with galaxies in every direction, denser than average, and spanning the sky as far as one could see. Its coherence emerges only from a distant vantage point, only when plotted in 3 dimensions across billions of light-years. In this sense, the Hercules-Corona Borealis Great Wall is both real and conceptual, both a genuine physical feature and a human attempt to describe immensity with the language of geometry and architecture. The discovery also highlights the role of new observational methods in expanding our cosmic perspective. Where early surveys relied on galaxies and clusters, the use of gamma-ray bursts pushed our reach deeper into the universe, revealing structures invisible through conventional means. Future surveys will refine this picture, perhaps mapping the Hercules-Corona Borealis Great Wall in detail, with next-generation telescopes capable of charting galaxies at extreme distances. Until then, it remains a mixture of revelation and mystery, a structure both seen and unseen, both measured and doubted. Philosophically, the wall is a mirror of our limitations. It shows that even with the most sophisticated theories and simulations, the universe retains the ability to surprise, to present scales and structures that defy neat categorization. It humbles our sense of certainty, reminding us that our models are provisional, contingent upon evidence, and always vulnerable to revision. The Hercules-Corona Borealis Great Wall is a symbol of the cosmos as inexhaustible, always larger, always stranger, always waiting to unfold another layer of immensity before our eyes. In the end, whether it is a single coherent wall or a grand alignment of filaments, the Hercules-Corona Borealis Great Wall represents the pinnacle of scale in the observable universe. It is a boundary marker, a place where theory falters and imagination must stretch. It is both a physical feature and a philosophical challenge, reminding us that the universe is not only more immense than we know, but more immense than we may ever fully grasp. To contemplate it is to look into the abyss of scale, to see the cosmos not as a sea of stars, but as a cathedral of walls and voids, vast beyond reckoning, enduring beyond comprehension. To see the largest structures in the universe is not to look through a telescope at a single galaxy, but to trace the distribution of countless galaxies across billions of light-years. The cosmic web, with its filaments, voids, and walls, cannot be glimpsed in an instant. It must be reconstructed painstakingly, piece by piece, like assembling a mosaic so large that one cannot see its outline until the final tiles are placed. Mapping the web is one of astronomy's greatest achievements, a project that has unfolded over decades as instruments have improved, redshift surveys have expanded, and theory has kept pace with observation. What began as speculation, that galaxies might form patterns beyond their immediate clusters, has now become one of the most visually and conceptually stunning portraits of the universe. a map of matter itself. The first great strides came in the latter half of the 20th century. For centuries, astronomers looked at the sky as a flat dome, a two-dimensional projection of stars and galaxies. The concept of depth, of three-dimensional cosmic geography, was largely missing. That changed with the advent of redshift surveys, which measured not only the positions of galaxies on the sky, but also their distances, inferred from the stretching of their light as the universe expanded. With these data, astronomers could plot galaxies in space, transforming the sky into a map of structures. In the 1980s, the CFA Redshift Survey produced one of the first three-dimensional slices of the universe, revealing vast filaments and voids, where galaxies were not randomly scattered, but arranged in a sponge-like pattern. The famous CFA Great Wall was one of the earliest hints that galaxies collect into coherent structures, far larger than clusters. The real revolution, however, came with the Sloan Digital Sky Survey, SDSS, launched in 2000. With its robotic telescope in New Mexico, SDSS embarked on an unprecedented project to measure the positions and redshifts of millions of galaxies. Over the next 2 decades, it produced the most detailed three-dimensional map of the universe ever assembled, revealing structures like the Sloan Great Wall and tracing filaments stretching hundreds of millions of light-years. When plotted, the data showed galaxies forming arcs, threads, and sheets surrounding immense voids, the exact pattern predicted by cosmological simulations. For the first time, humanity could see the universe as it really is on its largest scales. Not a random scatter, but an interconnected web spanning the sky. Mapping the web is not simply a matter of plotting points, however. Each galaxy is a marker of a deeper structure, a dot on the surface of an invisible scaffold of dark matter. Simulations such as the Millennium simulation and the more recent Illustris TNG project model, the evolution of billions of dark matter particles from the Big Bang to the present, showing how gravity sculpts them into filaments and nodes. When galaxies are added to these simulations, the match with observations is uncanny. The cosmic web emerges in both: vast sheets where filaments meet, deep voids between them, and clusters sitting like jewels at the intersections. Mapping the web, then, is not only observational, but theoretical. An interplay between what telescopes see and what computers predict, each refining the other. Different techniques have also expanded the map beyond galaxies. One powerful method involves the Lyman alpha forest, the absorption features in the spectra of distant quasars. As the light from a quasar passes through intergalactic hydrogen gas, it leaves a series of absorption lines that encode the distribution of matter along the line of sight. By collecting spectra from thousands of quasars, astronomers reconstruct a three-dimensional map of gas in the distant universe, extending the cosmic web picture back to times when galaxies were just beginning to form. This technique reveals that filaments existed as early as 2 billion years after the Big Bang, tracing the framework upon which later galaxies were built. The cosmic microwave background, CMB, also plays a role in mapping the web. Tiny fluctuations in the CMB mark the seeds of later structure, the primordial ripples that gravity amplified into the filaments and voids we see today. By comparing CMB maps from missions like Planck with galaxy surveys, astronomers can test how well our models of growth match reality. The agreement is remarkable. The same ripples imprinted on the sky nearly 14 billion years ago gave rise to the web of galaxies, now spanning billions of light years. Mapping, in this sense, is not only a chart of where galaxies are now, but a connection across time, a bridge between the infancy of the universe and its present maturity. Gravitational lensing has added yet another layer. Because light bends as it passes through mass, The shapes of background galaxies are subtly distorted by the gravitational fields of intervening structures. By measuring these distortions across wide areas of the sky, astronomers can map the distribution of dark matter directly, even where no galaxies are visible. These lensing maps reveal the same filamentary patterns traced by galaxies, confirming that dark matter is the true backbone of the cosmic web. The Dark Energy Survey, DES, for instance, has produced wide-field maps of lensing that align beautifully with simulations, showing the skeleton of the universe with dark matter as its bones. The process of mapping continues to evolve. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, set to begin operations soon, will record billions of galaxies, creating an even deeper and more detailed map of the cosmic web. The Euclid mission, launched by the European Space Agency, is already measuring weak lensing across vast swaths of sky, aiming to refine our understanding of dark matter and dark energy through the structure of filaments. These projects will push the map outward, tracing the web farther and with greater resolution, perhaps even clarifying whether immense anomalies like the Hercules-Corona Borealis Great Wall are coherent features or illusions of chance alignment. Philosophically, the act of mapping the cosmic web is a profound human endeavor. To draw maps is to impose order on the unknown, to transform the incomprehensible into something legible. Just as early explorers charted coastlines and continents, we now chart the universe itself, mapping not land or sea, but space and time. The cosmic web is our new geography. Its filaments are rivers, its walls are mountains, its voids are oceans of emptiness. In seeing it, we glimpse not only where galaxies are, but how the universe organizes itself, how the invisible scaffolding of dark matter gives shape to all that is luminous. The deeper we map, the more the universe resembles a pattern rather than a chaos. The threads of the web suggest order, connection, and structure across scales so vast they defy imagination. They also remind us that our place is small. The Milky Way is just one faint dot on one faint strand of one filament among countless others. Yet by mapping, by tracing, by plotting billions of galaxies into a grand lattice, we extend our reach across the cosmos. The map is both a picture and a mirror. A picture of what exists and a mirror of human curiosity, our refusal to leave the unknown uncharted. In the end, mapping the cosmic web is not only a scientific triumph, but also a philosophical one. It shows that the universe, however vast, can be understood in patterns, that what at first seems overwhelming can be revealed as structure. The cosmic web is the universe's handwriting across the darkness, and by mapping it, we begin to read the story of existence itself. As astronomers discover ever larger structures, from the Sloan Great Wall to the Hercules-Corona Borealis Great Wall, an unavoidable question arises. Is there a limit to how large structures in the universe can be? At what scale does the web of matter dissolve into homogeneity, smoothing out into the cosmic background? This question touches the foundations of cosmology itself, because our models of the universe rest on the assumption that beyond a certain size, matter is evenly distributed. The cosmological principle, one of the bedrock assumptions of modern astronomy, states that the universe should appear uniform when averaged over the largest scales. Without this principle, the equations of cosmology lose their elegance and predictive power. And yet, discoveries of billion light-year walls and 10 billion light-year anomalies seem to test the very boundaries of this assumption, leaving us to wonder, does the universe have limits? Or does it continue to surprise with structures of incomprehensible scale? The concept of a cosmic limit first arose when cosmologists considered the growth of structure after the Big Bang. In the beginning, the universe was nearly uniform, with only tiny fluctuations in density visible in the cosmic microwave background radiation. Over time, Gravity amplified those fluctuations, pulling matter into filaments and clusters. But because the universe has only existed for about 13.8 billion years, there's a maximum size to the regions that could have coherently collapsed under gravity. Simulations of cosmic evolution suggest that structures larger than about 1.2 billion light-years should be exceedingly rare. This boundary is sometimes called the end of greatness, the scale at which the universe should transition from structure to smoothness. On scales larger than this, galaxies should appear evenly distributed, without coherent features. And yet, observations have pushed against this theoretical boundary. The Sloan Great Wall, at 1.4 billion light-years, already slightly exceeded the predicted limit. The Hercules-Corona Borealis Great Wall, if it is indeed a coherent structure, stretches an order of magnitude beyond that, at nearly 10 billion light-years. Such discoveries have prompted deep unease. Are these truly single, coherent walls? Or are they statistical illusions, alignments of smaller structures that our eyes interpret as one? If they are genuine, then either the cosmological principle must be revised, or our understanding of how structure grows in the presence of dark matter and dark energy must be incomplete. Part of the problem lies in how we define structure. The cosmic web is inherently hierarchical, with filaments connecting to walls, walls merging into superclusters, and superclusters into chains that extend farther and farther. At what point does one end and another begin? Is the Hercules-Corona Borealis Great Wall really a single structure? Or is it simply a convenient label for a region of space with an unusual density of filaments? This ambiguity mirrors challenges in other sciences. Where does a forest end and another begin? Where does a mountain range become a plateau? Human categories are convenient, but nature often refuses to conform neatly to them. Even so, the question of cosmic limits remains urgent. If the universe is truly homogeneous at the largest scales, then structures like the Hercules-Corona Borealis Great Wall must be statistical outliers. If homogeneity breaks down, however, the implications are profound. It could mean that the universe has preferred directions or scales, violating isotropy. It might hint at physics beyond the standard model of cosmology, perhaps new kinds of dark matter, or interactions in the early universe that seeded larger ripples than expected. Some theorists have even speculated that such immense structures could be signatures of cosmic inflation, the exponential expansion thought to have occurred in the universe's first moments. Inflation should have smoothed the cosmos, but small variations in how it unfolded could, in principle, leave behind relics on scales larger than expected. There is also the question of the observable universe itself. We can see only as far as light has traveled since the Big Bang, about 46 billion light-years in radius. Beyond that horizon, the universe may continue, perhaps infinitely, perhaps in ways we cannot imagine. Structures larger than the observable universe may exist, but remain forever beyond our sight, hidden not by distance alone, but by the finite speed of light. In this sense, our question about limits may be more about the limits of our perception than about the universe itself. We can only map what we can see. What lies beyond remains speculation, a realm of philosophy and imagination, as much as science. Philosophically, the search for cosmic limits reflects humanity's perennial desire for boundaries. We ask, how far does the universe go? How large can it be? Is there an edge, a maximum, a ceiling? And each time, the universe has replied with silence, or with surprises that expand our sense of scale. In ancient times, people imagined the cosmos as a dome over the Earth. Later, it was the solar system, then the galaxy, then the observable universe. Each step revealed structures larger than expected, forcing us to revise our boundaries. The Sloan Great Wall and the Hercules-Corona Borealis Great Wall are just the latest in this lineage of humbling revelations. They remind us that limits are often projections of our imagination, not realities imposed by nature. At the same time, the idea of limits is essential for science. Without the cosmological principle, cosmology would be unmoored, unable to generalize the properties of the universe. The challenge is to reconcile the principle with the anomalies, to find a framework that allows for statistical outliers without discarding the larger truth of homogeneity. Many cosmologists believe this is possible, that structures like the Hercules-Corona Borealis Great Wall are extreme but permissible within the probabilistic nature of the universe. Others argue that they point to cracks in the foundation, signs that deeper physics awaits discovery. Either way, the debate is fruitful, driving new observations and new theories. Looking forward, future surveys will push the question further. The Vera C. Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope will map galaxies across unprecedented volumes of space, clarifying whether immense features are coherent structures or chance alignments. Gamma-ray burst catalogues will expand, refining the evidence for walls like the Hercules-Corona Borealis. Gravitational wave detectors may even add new ways to trace cosmic structure, using the mergers of black holes and neutron stars as beacons across space-time. Each advance will sharpen the boundary between structure and smoothness, between the patterned and the homogeneous. In the end, the possible limits of the universe may not be limits at all, but thresholds of perception. The cosmic web is vast, perhaps infinite, and what we see are only fragments, patterns emerging from our finite vantage point. Whether the largest structures we observe are outliers or signs of deeper laws, they remind us that the cosmos is always larger than our categories, always pushing back the horizons of understanding. To speak of limits is to acknowledge both our curiosity and our ignorance, both our drive to measure and our inability to comprehend infinity. Perhaps the ultimate answer is that the universe has no limits in structure, only in our capacity to see. Or perhaps it does. A statistical ceiling, an end of greatness beyond which all is smooth. Either way, the search itself is revelatory. In confronting the largest structures, we confront the grandeur of existence, the immensity of time and space, and the humility of our place within them. The Sloan Great Wall, the Hercules-Corona, Borealis, the cosmic filaments and voids. These are not just astronomical features, but reminders that the universe is a cathedral of immensity, one in which our questions echo endlessly, unanswered but never futile. For in asking, we stretch our imagination to match the cosmos, and in stretching, we come a little closer to the infinite. Hypergiant stars, cosmic behemoths. When we think of stars, we often imagine them as distant pinpricks of light scattered across the night sky. Yet among those points are giants so vast that they defy human comprehension, swelling to sizes that dwarf our own sun thousands of times over. These are the hypergiants, the largest known stars in the universe, and among them shine names that have become legendary in modern astronomy. UY Scuti, VY Canis Majoris, and Stevenson 2-18. Each is a cosmic behemoth, a star so swollen and luminous that the scale of its dimensions forces us to rethink our place in the cosmos. UY Scuti, discovered in the constellation Scutum, was long considered the largest known star by radius. Located about 9,500 light-years from Earth, it is a red hypergiant with a radius estimated at more than 1,700 times that of the Sun. To put this in perspective, if UY Scuti were placed at the center of our solar system, its surface would extend past the orbit of Jupiter, engulfing Mercury, Venus, Earth, Mars, and even the asteroid belt. The sheer immensity of such a star defies easy visualization. Our entire world, all of human history, would be a microscopic speck deep within its interior. And yet, UY Scuti is only one of several rivals for the title of largest star, its position on the list shifting as measurements improve and as other hypergiants step into view. VY Canis Majoris, in the constellation of Canis Major, is another red hypergiant famous for its gargantuan proportions. Once thought to be the largest known star, it has a radius in the range of 1,400 to 1,500 times that of the Sun. Though slightly smaller than UY Scuti by current estimates, VY Canis Majoris compensates with its extreme luminosity, shining nearly 300,000 times brighter than the Sun. Observations reveal that it is surrounded by vast clouds of material shed through powerful stellar winds. These outflows testify to its instability, a hypergiant at the end of its life, shedding mass so rapidly that its days are numbered. The star's history reminds us that hypergiants are not only enormous, but volatile, living short, tumultuous lives that often end in violent supernova explosions. And then there is Stephenson 2-18, a star so immense it has pushed the definition of hypergiants to its limit. Found within the Stephenson 2 cluster in the constellation Scutum, this red hypergiant has been measured at nearly 2,150 times the radius of the Sun, making it one of the largest stars ever identified. Its sheer scale is staggering. Place Stephenson 2-18 at the center of the solar system, and its surface would extend almost to the orbit of Saturn. A volume comparison reveals that billions of suns could fit inside it, with room to spare. Yet despite its immensity, Stephenson 2-18 would be invisible to the naked eye from Earth, buried within clouds of interstellar dust. Its discovery required careful infrared observation, a reminder that the universe often hides its greatest wonders behind veils of obscurity. Hypergiants like these are not only marvels of scale, but also puzzles of physics. How can a star grow so large without tearing itself apart? What prevents its immense gravity from collapsing it inward, or its outward radiation from blasting it apart? The balance is precarious, a tug of war between gravity pulling inward and radiation pressure pushing outward. In hypergiants, this equilibrium exists at the very edge of stability. Their outer layers are tenuous, extended, and unstable, prone to eruptions and shedding. They burn fuel at prodigious rates, consuming in a few million years what smaller stars like the Sun take billions to use. Their immensity is both a triumph of stellar physics and a guarantee of brevity. They are destined to live fast and die young. Philosophically, hypergiants embody the tension between grandeur and fragility. They are among the most majestic objects in the universe, their size is so vast that they challenge the imagination, and yet they are also among the least stable. Unlike small stars that endure for billions of years, hypergiants are ephemeral, flashing briefly across cosmic time before collapsing into catastrophic ends. They remind us that immensity is not immortality, that greatness often carries within it the seeds of its own destruction. UY Scuti, VY Canis Majoris, Stephenson 2-18. These stars are titans, but titans fated to fall. They also highlight the limits of human perception. To the unaided eye, these stars are faint or invisible, hidden behind dust or too far away to shine prominently in our skies. Yet when measured with the tools of modern astronomy, their true scale emerges, revealing structures that eclipse imagination. The contrast is humbling. Stars so vast that they could swallow our solar system whole, and yet so distant and shrouded that they escape our sight. It is a reminder that the universe is filled with wonders beyond our senses, waiting only for us to look deeper. These hypergiants are also keys to understanding the extremes of stellar evolution. By studying them, astronomers test the boundaries of how stars live and die, probing the physics of nuclear fusion, radiation pressure, and mass loss. They challenge models of stellar structure, forcing refinements to theories that must account for stars at the very edge of stability. They are not merely curiosities, but essential laboratories, their immensity pressing against the limits of what matter and energy can do within the confines of gravity. In the stories of UY Scuti, VY Canis Majoris, and Stephenson 2-18, we see both the wonder and the tragedy of hypergiants. They are magnificent in scale, yet fleeting in time. They reveal the richness of the cosmos, yet also its indifference, reminding us that beauty and destruction often walk hand in hand. To contemplate them is to look into the extremes of existence, to imagine not only size but also impermanence, to see the cosmos not as stable, but as a place of constant creation and loss. The discovery of hypergiant stars like UY Scuti, VY Canis Majoris, and Stephenson 2-18 naturally leads to a profound question. What is the upper limit to stellar size? How large can a star become before the laws of physics intervene? Before gravity and radiation, mass and instability conspire to set a ceiling on immensity? This question is not simply a curiosity, but a probe into the fundamental principles of stellar evolution, for hypergiants push stars to the edge of possibility, balancing on a razor's edge between cohesion and collapse. Stars are born within giant molecular clouds, where gravity pulls hydrogen gas into denser clumps. When enough mass accumulates, nuclear fusion ignites at the core, balancing gravity with radiation pressure. For most stars, like our Sun, this balance is stable for billions of years. But for hypergiants, the story is different. Their immense mass means their cores burn with ferocious intensity, consuming hydrogen in only a few million years. The same radiation that sustains them also drives their instability, puffing up their outer layers into tenuous envelopes that extend across billions of kilometers. The question of how big a star can get is therefore not just about size, but about how long such a precarious balance can be maintained. Astronomers distinguish between two limits on stellar immensity: the mass limit and the radius limit. The mass limit is determined by how much material a forming star can accumulate before radiation pressure blows gas away, preventing further growth. The radius limit, by contrast, concerns how far a star's atmosphere can expand without dispersing into space. Hypergiants approach the maximum in both categories, showing us the outer boundary of stellar possibility. For mass, the ceiling seems to lie around 150 to 200 solar masses. Above this, stars become unstable because the radiation from their cores is so intense that it counteracts gravity, blasting away accreting material. This is known as the Eddington limit, the point at which radiation pressure equals gravitational pull. Some stars may briefly exceed this mass, particularly in dense star-forming regions, but they quickly shed matter through powerful winds, bringing them back under the threshold. Thus, while we can imagine stars more massive than 200 suns, the universe itself conspires to strip them down, enforcing a practical maximum. The radius limit is more complex. Unlike mass, which is capped by the Eddington limit, a star's radius can swell to enormous proportions, particularly in the late stages of its life. Hypergiants like Stephenson 2-18 have radii more than 2,000 times the Sun's, their atmospheres inflated by unstable energy flows. But these envelopes are extremely diffuse, with densities lower than the vacuum of Earth's laboratories. They are more like extended veils of gas than solid surfaces. Indeed, if one were somehow to stand within the atmosphere of such a star, the boundaries between star and space would be difficult to perceive. This fuzziness makes size itself a slippery concept for hypergiants, since their edges are not well defined. Some astronomers argue that stars like Stephenson 2-18 are not truly larger than others in a meaningful way, but simply more distended, their outer layers on the brink of dispersal. Beyond these physical constraints, hypergiants face another limiting factor: time. The larger the star, the shorter its life. A sun-like star may burn for 10 billion years, but a hypergiant of 100 solar masses may last only a few million. At such scales, immensity is fleeting, a brief flare in the cosmic timeline. In this sense, the question of how big a star can get is inseparable from how long it can survive. The universe may permit temporary titans, but it quickly reclaims them, recycling their mass in spectacular supernovae. There is also the intriguing possibility of population 3 stars, the first generation of stars formed after the Big Bang. Composed almost entirely of hydrogen and helium, without the heavier elements that drive winds and instabilities. These stars may have grown far larger than any stars we see today. Some models suggest they reached hundreds, perhaps even thousands of solar masses, before collapsing into black holes. If so, the largest stars in cosmic history may already have come and gone, leaving behind only their remnants and the heavy elements they forged. Modern hypergiants may be impressive, but they may be mere echoes of even greater titans that lit the universe's earliest dawn. Philosophically, the limits of star size remind us that nature is not infinite, even in its grandeur. There are thresholds, boundaries drawn by physics, beyond which immensity collapses into instability. Hypergiants are expressions of excess, stars that have grown too large for their own good, and their instability is proof of that. They embody the paradox of limit and transgression. They exist precisely because the universe allows stars to push against boundaries. But they perish because those boundaries cannot be broken. And yet the fascination remains. How big can a star get? The answer, at least for the present universe, seems to be about 200 times the Sun in mass, and about 2,000 times the Sun in radius. Beyond that, physics unravels, and stars collapse under their own contradictions. But the deeper truth is that the very act of asking stretches our imagination, compelling us to think on scales where human metaphors falter. If our Sun is a hearthfire, then hypergiants are cosmic bonfires, raging across space with the fury of creation itself. They are reminders that even within limits, the universe produces spectacles of immensity that eclipse comprehension. In the end, the largest stars are not the ones that endure, but the ones that burn so brightly that their lives must end quickly. Their very size guarantees their demise, and their grandeur is bound inseparably to their fragility. The question of how big stars can get is thus also the question of how brief they must be, how beauty and destruction entwine at the edge of possibility. The story of hypergiant stars is not merely about their size, but about their astonishingly brief and turbulent journeys from birth to death. These cosmic behemoths are the aristocrats of the stellar world, born with immense wealth in mass and energy, but condemned to live fast and die young. Where the Sun can enjoy a steady existence for 10 billion years, a hypergiant may last only a few million, a blink of an eye in cosmic terms. Their lives are epics written in fire, beginning with violent births, proceeding through unstable adolescence, and ending in catastrophic deaths that echo across the universe. Hypergiants begin their existence in the densest parts of giant molecular clouds, the stellar nurseries where gravity pulls gas and dust into collapsing clumps. Because they are so massive, hypergiants form rapidly, gathering material in torrents that would overwhelm smaller stars. Within just a few 100,000 years, they ignite nuclear fusion in their cores, starting with hydrogen into helium. This stage, known as the main sequence, is familiar to all stars, but in hypergiants it is brief and furious. Their immense masses mean that their cores reach extreme pressures and temperatures, causing fusion to proceed at breakneck speed. What the Sun burns in billions of years, They consume in a fraction of that time. As they age, hypergiants evolve quickly. Once the hydrogen in their cores is exhausted, they begin fusing heavier elements, helium into carbon and oxygen, then carbon into neon, magnesium, and silicon. Each stage happens faster than the one before, like a clock ticking more frantically as the end approaches. In the final days, fusion of silicon produces iron, the ultimate dead end of stellar alchemy. Unlike lighter elements, iron cannot release energy through fusion, and so the hypergiant's core faces an inevitable collapse. But long before that final moment, the star shows signs of its instability. One of the hallmarks of hypergiant life is their instability. Their outer layers, extended and tenuous, are prone to eruptions and shedding. Powerful stellar winds strip away mass at prodigious rates, carving vast nebulae around them. VY Canis. Majoris, for example, is surrounded by great clouds of gas ejected in violent outbursts. These winds are not gentle breezes, but hurricanes of matter, carrying away the equivalent of an Earth's mass every year. Over time, these outflows sculpt the star, reducing its mass and influencing its fate. They also enrich the interstellar medium, seeding space with heavy elements that will one day form new stars and planets. Hypergiants in this sense are both creators and destroyers, consuming matter at their cores while dispersing it back into the galaxy. Their instability can also manifest in pulsations and variability. Many hypergiants are luminous variable stars, their brightness waxing and waning as their outer layers expand and contract. These cycles can last months or years, providing astronomers with valuable insights into their inner workings. Yet beneath the beauty of their variability lies the shadow of mortality. Each pulsation is another symptom of the delicate balance that cannot last. The end of a hypergiant's life is among the most spectacular events in the cosmos. A supernova explosion. When the core collapses under its own gravity, it triggers a rebound that blasts the outer layers into space with incredible energy. In seconds, the star releases as much energy as the sun will emit in its entire lifetime. For a brief time, the supernova can outshine an entire galaxy, visible across millions of light years. These explosions are not only awe-inspiring, but also essential to cosmic evolution, for they forge the heaviest elements, gold, uranium, and others, and scatter them across the galaxy. Every atom of iron in our blood, every trace of gold in our rings, was once forged in the death throes of a massive star. Hypergiants, in dying, give life to future worlds. Some hypergiants may die even more violently, collapsing directly into black holes, or producing gamma-ray bursts, the most powerful explosions known. If their cores spin rapidly enough, the collapse can form jets of relativistic particles that blast out along their poles, releasing torrents of energy that briefly outshine the universe itself. Such events are rare but terrifying, capable of sterilizing entire regions of space, if they occur close enough to inhabited worlds. They remind us that the grandeur of hypergiants carries not only beauty, but danger. Their deaths, as destructive as their lives, are luminous. Philosophically, the life and death of hypergiants resonate with themes of brevity, excess, and transformation. They are born immense, burn furiously, and die young. They embody the idea that greatness comes with cost, that to shine too brightly is to shorten one's time. Their deaths, though catastrophic, are also creative, scattering the raw materials for new stars, planets, and perhaps life. In their brief, brilliant lives, hypergiants perform the ultimate alchemy, transforming hydrogen and helium into the building blocks of biology, then dispersing them into the cosmos. Without them, the universe would be barren of complexity. In their deaths, they ensure the possibility of our existence. Their story also highlights the tension between human and cosmic timescales. To us, a million years is an eternity. To a hypergiant, it is a fleeting heartbeat. Their lifespans are too short to be stable across cosmic epochs. Many we observe today may already be gone, their light still crossing space toward us, while their remnants lie as neutron stars or black holes. To study hypergiants is to peer into a fragile moment, to catch them in their blaze before they vanish. In the end, the life and death of hypergiants remind us that the universe is not static, but dynamic, not eternal, but transient. Stars live and die, galaxies evolve, structures grow and dissolve. Hypergiants are the most dramatic actors in this play, stars that embody excess and impermanence. Their lives are brief but unforgettable, their deaths violent but transformative. To contemplate them is to glimpse both the beauty and the tragedy of existence, written on a cosmic scale. If hypergiants are the largest stars in the universe, they are also among the most unstable. Their immensity is not a mark of permanence but of fragility, for their outer layers are so extended and tenuous that they can be lost to space in vast, sweeping winds. These stellar winds, driven by the enormous luminosity and radiation pressure of hypergiants, are not like the solar wind of our sun. Where the sun's wind carries away a millionth of its mass per year, hypergiants may lose an Earth's mass annually, or even a Jupiter's mass over the course of their short lives. The result is a continual shedding, a storm of matter so powerful that it reshapes both the stars themselves and their surroundings. The physics of these winds begins at the surface, where radiation pressure acts on atoms and dust grains. In most stars, gravity dominates, holding the outer layers in place. But in hypergiants, the balance tips precariously. Their luminosity is so extreme, hundreds of thousands of times that of the sun, that photons exert a tangible force, pushing material outward. Every atom in the upper layers feels the tug of light, and when this pressure surpasses the star's already weakened gravitational grip, material is cast off into space. This process is amplified by pulsations, shock waves, and magnetic activity, creating a turbulent, chaotic atmosphere in which gas and dust are constantly in motion. The winds of hypergiants create spectacular nebulae, glowing shells of material that testify to their instability. VY Canis Majoris, for instance, is enveloped in a sprawling cloud of gas and dust, ejected over the past few 100,000 years. Observations reveal arcs, knots, and filaments, evidence of episodic eruptions rather than steady outflow. These irregularities suggest that hypergiants do not lose mass quietly, but in fits and bursts, as though their outer layers cannot decide whether to cling to the star or break free. The result is a complex circumstellar environment, rich in heavy elements, that will one day mix into the interstellar medium. These winds are not only beautiful, but essential to galactic ecology. Hypergiants forge heavy elements in their cores and disperse them through their winds, enriching their surroundings long before their final supernova, deaths. The carbon, oxygen, and nitrogen they shed become part of future stars and planets. In this sense, their instability is creative as well as destructive, a form of recycling that ensures the universe grows richer with each generation of stars. Without such stellar winds, galaxies would remain poor in the elements necessary for life. Thus, the very instability of hypergiants is a condition of cosmic fertility. Instability, however, also hastens their demise. By losing mass so rapidly, hypergiants alter their evolutionary paths. Some may shed so much material that they avoid the most extreme supernovae, collapsing quietly into black holes instead. Others may explode prematurely, their outer layers stripped to the point where the core can no longer maintain equilibrium. In both cases, the winds shorten their already brief lives, making them fleeting presences in the cosmic timeline. Where the Sun will live serenely for billions of years, hypergiants rage for only a few million before collapsing under the weight of their contradictions. Astronomers observe these winds in multiple ways. In visible light, they appear as diffuse nebulae. In infrared, they glow with the heat of dust grains carried away from the star. In radio wavelengths, they reveal themselves as molecular gas, expanding outward at tens of kilometers per second. Each wavelength paints a different picture, and together they show the scale of the outflows. In some cases, the mass lost can amount to tens of solar masses over a hypergiant's short lifetime. Such prodigious shedding ensures that no hypergiant ends its life as it began. Each is profoundly reshaped by the storms it generates. Pulsations add to the drama. Hypergiants are often luminous variable stars, their outer layers expanding and contracting in cycles. These pulsations create shock waves that propagate through their atmospheres, further destabilizing them and enhancing mass loss. Some stars brighten and fade predictably, while others flicker erratically, a sign of chaotic processes at work in their interiors. The result is a restless life, marked not by stability, but by continual change. Hypergiants live not as serene giants, but as turbulent beacons, their surfaces boiling, and their atmospheres in constant flux. Philosophically, the instability of hypergiants is as compelling as their immensity. They remind us that grandeur does not imply permanence, that even the mightiest can be fragile. Their brilliance is purchased at the cost of stability, their size at the cost of longevity. They embody the paradox that the most extraordinary phenomena are often the most fleeting. To see a hypergiant is to see excess pushed to its breaking point, to witness a star attempting to be more than the laws of physics comfortably allow. Their winds are not signs of weakness, but of the immense forces tearing at their cores, the struggle between light and gravity written in the language of turbulence. The winds of hypergiants also shape the environments into which they will die. By carving out cavities and enriching nearby gas, they set the stage for the eventual supernova explosion. When that final detonation comes, it will expand into a medium already prepared, lighting up shells and filaments in complex patterns. In this way, instability does not end with the star, but echoes outward, influencing how its death will appear to observers millions of years in the future. Looking forward, the study of hypergiant winds and instability is more than an exercise in stellar physics. It is a window into the cycle of matter in the universe. Observatories, like the James Webb Space Telescope, are now capable of peering through the dust around these stars, tracing their outflows with unprecedented precision. Radio arrays like ALMA can map the gas they shed in exquisite detail, revealing how instability sculpts their surroundings. Each observation brings us closer to understanding not only the stars themselves, but the larger processes of galactic enrichment. In the end, hypergiants are not merely vast stars, but ongoing acts of creation and destruction. Their stellar winds are both the symptom of instability and the mechanism of renewal, tearing away their mass while seeding the cosmos with the ingredients for new worlds. To contemplate them is to recognize that instability itself can be fertile, that fragility can lead to abundance. The storms of hypergiants remind us that the universe is built not on permanence, but on transformation. That even in their collapse, the mightiest stars contribute to the endless cycle of cosmic life. Every story of a hypergiant star, however majestic, must end in fire. These colossal stars live fast and burn furiously, consuming their fuel at such prodigious rates that they have no chance of quiet retirement. While smaller stars like our Sun will fade gently into white dwarfs, hypergiants are doomed to die in some of the most violent explosions the cosmos can produce. Their ends are not only dramatic, but transformative, reshaping galaxies, forging elements, and sometimes leaving behind black holes that endure for eons. The death of a hypergiant is both a catastrophe and a gift, a final convulsion that scatters the seeds of new worlds across the galaxy. The path to that end begins with the exhaustion of fuel. In their brief lifetimes, hypergiants cycle rapidly through the stages of nuclear fusion, burning hydrogen into helium, helium into carbon and oxygen, and onward through neon, magnesium, silicon, and eventually iron. Each successive stage burns more quickly, until the final phase of silicon fusion, which lasts only a matter of days. At the core of the star, temperatures reach billions of degrees, but even this furnace cannot fuse iron into heavier elements without consuming energy rather than releasing it. With no new source of power to oppose gravity, the balance that has sustained the star collapses. What follows is one of the most extraordinary events in nature: core collapse. In less than a second, the core of a hypergiant implodes, shrinking from thousands of kilometers across to just tens. Protons and electrons are crushed into neutrons, and the density of the core reaches that of an atomic nucleus. The outer layers, unsupported, fall inward, striking the rebounding core and producing a shock wave. This shock, powered by a flood of neutrinos escaping from the collapsing core, rips outward, tearing the star apart. The hypergiant explodes in a supernova, outshining an entire galaxy and releasing more energy in moments than the Sun will in its entire 10 billion-year life. The light of such explosions travels across millions of light-years, sometimes bright enough to be seen in the daytime sky from Earth. Ancient civilizations recorded such events. The Chinese chronicles of 1054 CE describe the supernova that created the Crab Nebula, though that progenitor was likely a less massive star than a hypergiant. Still, the principle is the same. The death of a giant sends a beacon across the cosmos, announcing the end of one life and the beginning of countless others. Hypergiant supernovae are among the brightest, their titanic masses producing cataclysms on scales that defy imagination. Not all hypergiant deaths are alike. Some collapse into neutron stars, ultra-dense remnants no more than 20 kilometers across, yet heavier than the Sun. Others, particularly the most massive, collapse directly into black holes, their cores imploding beyond the event horizon, leaving behind regions from which not even light can escape. In rare cases, if the star is rotating rapidly and its magnetic fields align just right, the collapse can trigger gamma-ray bursts, jets of relativistic particles blasting out at near light speed, among the most energetic phenomena in the universe. For a few seconds, such a burst can release more energy than all the stars in the observable universe combined. Though aimed narrowly, these bursts can sterilize entire regions of space. A stark reminder that the death of giants is not only creative, but dangerous. Yet for all their violence, hypergiant deaths are also profoundly constructive. Their explosions scatter the heavy elements forged in their cores into the interstellar medium. Iron, calcium, silicon, gold, uranium. These are the ashes of hypergiants. Every atom of iron in your blood, every trace of gold in a ring, every grain of calcium in a seashell was once forged in a star that died in such an explosion. Without hypergiant supernova, the universe would lack the diversity of elements necessary for life. They are alchemists on a cosmic scale, transmuting the simplest elements of the Big Bang into the rich chemistry of planets and biology. Supernova remnants also shape galaxies. The shock waves plow through interstellar gas, compressing it into new star-forming regions. In this way, the death of one generation seeds the birth of the next, a cycle of stellar ecology that links every star to its predecessors. Entire clusters of stars may form in the wake of a hypergiant's death, their chemistry enriched by the elements it produced. Thus, while the hypergiant perishes, its influence extends for billions of years, imprinted on the stars, planets, and even living beings that follow. Philosophically, The end fate of hypergiants is a meditation on impermanence and transformation. Their deaths are violent beyond imagining, yet they are also acts of creation, without which the universe would be sterile. They embody the paradox of destruction as genesis, of loss as renewal. They remind us that endings are not final, but are woven into the larger fabric of continuity. In the death of a hypergiant, the cosmos writes its most dramatic chapter, one that is echoed in the composition of every rock, every drop of water, every cell in our bodies. We are, quite literally, the children of hypergiant deaths. And yet, there is also humility in contemplating their fate. Hypergiants live for only a few million years, a fleeting moment compared to the age of the universe. Many of the hypergiants we observe today may already be gone, their light still on its way to us, while their remnants lie as black holes or neutron stars. To gaze at a hypergiant is often to see a ghost, an image of a star that may have already met its fiery end. The universe is full of such ghosts, reminders that even the brightest lights are transient. Looking ahead, astronomers continue to search for signs of imminent hypergiant explosions. Some candidates, like Betelgeuse in Orion, though technically a red supergiant rather than a hypergiant, have attracted attention for unusual dimming events that hint at instability. While Betelgeuse's explosion may still be thousands of years away, its example shows how eagerly we await the spectacle of a nearby supernova. If a hypergiant in our galactic neighborhood were to explode, it would be one of the most extraordinary astronomical events in human history, visible even in daylight, a reminder that the universe is still alive with drama. In the end, the fate of hypergiants is to burn briefly, die violently, and scatter their remains across the galaxy. They are cosmic fireworks, ephemeral but transformative, embodying both grandeur and fragility. Their lives are warnings about excess, about the cost of burning too brightly. But their deaths are gifts, providing the elements that make life and worlds possible. They are both destroyers and creators, their final breaths seeding the cosmos with the richness of matter. To reflect on their fate is to understand not only stars, but ourselves, for in their deaths lies the story of our own beginnings. Wolf-Rayet stars. Stars that burn too bright. Among the most extreme and enigmatic stars in the cosmos are the Wolf-Rayet stars. They are not gentle suns like our own, nor vast red giants with swollen atmospheres, but stripped-down titans, the exposed hearts of massive stars that have shed their outer layers. What remains is a blazing naked core, hotter, brighter, and more unstable than nearly any other object in the stellar zoo. To behold a Wolf-Rayet star is to witness a furnace at full blast, a star with no veil, its secrets laid bare in radiation, winds, and fury. These stripped stellar cores represent a late and violent stage in stellar evolution, a brief and furious interval before collapse into supernova or black hole. The story of a Wolf-Rayet star begins with a massive progenitor, often 20 or more times the mass of the Sun, that has exhausted much of its hydrogen fuel. As the star evolves, intense stellar winds, pulsations, or interactions with a close companion strip away its hydrogen envelope. In some cases, the stripping is gradual, carried away by relentless winds driven by the star's immense radiation. In others, it is violent, ripped away in outbursts, or stolen by a binary partner. Whatever the mechanism, the result is the same. The outer layers of hydrogen are gone, revealing the deeper regions where helium fusion now rages. What emerges is unlike any ordinary star. A Wolf-Rayet surface temperature can soar to 50,000 to 200,000 Kelvin, making it dozens of times hotter than the Sun. Its light floods space with ultraviolet radiation, ionizing gas in its surroundings, and creating glowing nebulae that testify to its presence. Because the hydrogen veil is absent, the star's spectrum reveals broad emission lines from helium, nitrogen, carbon, and oxygen. Heavy elements dredged up from the fusion-fueled interior. These spectral fingerprints are so distinctive that Charles Wolf and Georges Rayet, who first identified these stars in 1867, recognized them immediately as a new and peculiar class. To this day, their names define the category. The stripping of these stars reveals a deep truth about stellar evolution, that stars are not static spheres of gas, but dynamic entities, shedding and transforming as they burn. A Wolf-Rayet star is a reminder that what we see in the night sky is often a facade, a temporary phase. The blazing surface of a main sequence star conceals the layers within, but a Wolf-Rayet is the layers laid bare, its inner workings exposed to the cosmos. What we observe is no longer a youthful star in balance, but an elder nearing its end, its core erupting into brilliance as it approaches collapse. Stripped cores also mean stripped futures. By losing their hydrogen envelopes, Wolf-Rayet stars evolve differently than giants that retain theirs. They bypass the bloated red supergiant stage and instead march directly toward explosive ends, often producing Type 1b or IC supernovae, in which the usual hydrogen lines are absent from the spectrum. In some cases, their collapse may trigger long gamma-ray bursts, the most energetic explosions known, powered by rapidly rotating Wolf-Rayet cores collapsing into black holes. Thus, the act of shedding their outer layers not only defines their present state, but also shapes their destiny, linking the peculiarities of their spectra to the fireworks of their deaths. But these stripped cores are not only extreme, they are brief. The Wolf-Rayet phase typically lasts less than 1 million years, a fleeting chapter in the life of a massive star. This transience explains their rarity. At any given time, only a few hundred Wolf-Rayet stars are known in the Milky Way, compared to hundreds of billions of ordinary stars. Their scarcity adds to their mystique, making each one a precious laboratory for studying the upper limits of stellar physics. Philosophically, Wolf-Rayet stars embody the concept of exposure. Unlike most stars, they are not cloaked in protective atmospheres, but stripped to their essence. They shine as metaphors for truth laid bare, brilliance unhidden, intensity unconcealed. Yet this exposure also makes them fragile. Their nakedness is a sign of vulnerability, a stage that cannot last. They are stars that burn not with serenity but with desperation, consuming themselves at breakneck speed, unable to moderate their brilliance. They remind us that sometimes what burns brightest does so because it has little time left to burn at all. In some cases, stripped stellar cores emerge not through winds alone, but through companionship. In binary systems, one star may siphon material from the other, peeling away its hydrogen layers and leaving behind a Wolf-Rayet. This process highlights the role of relationships in stellar evolution. Stars do not always live or die alone. They can profoundly alter each other's fates, transforming stable giants into stripped-down engines of instability. Some of the most famous Wolf-Rayet stars, such as those in binary systems with O-type companions, display complex interactions, with winds colliding to produce dazzling arcs of X-rays and dust spirals that glow in infrared. These pairings remind us that stellar evolution is not solitary, but social, a dance of interactions that can reshape both partners. To stand before a Wolf-Rayet star, if such a thing were possible, would be to confront raw energy. Its surface would seethe with light and radiation, its winds howling outward at thousands of kilometers per second. Space around it would glow with ionized gas, carved into intricate nebulae like the Crescent Nebula surrounding WR-136. These are not stars as we usually imagine them, but cosmic furnaces in overdrive, their very surfaces unstable, their very existence a sign of extremes. In the end, Wolf-Rayet stars as stripped stellar cores reveal the universe's appetite for variety. Stars do not follow a single path but branch into multiple destinies, some serene, some violent, some hidden, and some bare. The Wolf-Rayet is the most exposed of all, its life a short but spectacular blaze. It is the raw core of a giant laid open to the sky, a reminder that even in destruction there is beauty, and even in brevity there is brilliance. If Wolf-Rayet stars are stripped to their cores, they are also unleashed in their power. With their hydrogen envelopes gone, their energy output is no longer moderated or veiled. What we see is raw luminosity, the naked brilliance of nuclear fusion operating at full tilt. Wolf-Rayet stars rank among the most luminous objects in the Milky Way, shining hundreds of thousands to millions of times brighter than the sun. Their light and radiation saturate their surroundings, ionizing entire nebulae, blowing bubbles in the interstellar medium, and sculpting the cosmos with invisible force. To grasp their output is to realize that these stars are not passive ornaments in the sky, but engines of galactic change. The sheer luminosity of a Wolf-Rayet star is staggering. A single one can outshine entire clusters of ordinary stars, bathing space around it in ultraviolet radiation. This energy is not just a spectacle. It actively reshapes the environment. Ultraviolet photons stream outward, ionizing gas for dozens of light years in every direction. Clouds of hydrogen become glowing H2 regions, lit from within by the star's radiation. Observers with telescopes see luminous shells and glowing arcs, testimony to the immense pressure these stars exert on their surroundings. This enormous output also drives their legendary stellar winds. Radiation pressure from photons slamming into atoms and dust grains accelerates matter outward at thousands of kilometers per second. These winds are so powerful that they can strip away several solar masses of material over the short lifetime of a Wolf-Rayet. In some cases, the outflows generate structures of haunting beauty, such as the spiral pinwheel nebulae seen around binary Wolf-Rayet systems, where colliding winds carve dust into patterns like cosmic whirlpools. Each spiral turn marks another cycle of the binary orbit, a celestial clock etched in starlight and dust. What makes Wolf-Rayet stars unique in their energy output is not only quantity but quality. Their radiation peaks in the ultraviolet and extreme ultraviolet, meaning they emit vast amounts of high-energy photons. These photons are capable of ionizing not only hydrogen, but also helium and heavier elements, stripping electrons and heating gas to tens of thousands of degrees. This makes Wolf-Rayet stars vital in shaping ionization fronts in galaxies. Regions with Wolf-Rayet stars glow differently than those lit by ordinary O-type stars, marked by emission lines of helium, nitrogen, carbon, and oxygen. Entire galaxies can bear their signatures, with spectral features that betray the presence of Wolf-Rayet populations, even when the stars themselves cannot be resolved individually. The energy output also has consequences for the stars' own lives. By blasting away their outer layers, Wolf-Rayet stars accelerate their march toward collapse. They are, in essence, consuming themselves from both within and without. Fusion at the core rapidly depleting fuel, while radiation at the surface strips away mass. Their brilliance is both a symptom of vitality and a sign of imminent death. They are stars that shine too brightly to last, their energy an extravagant expenditure that guarantees brevity. Wolf-Rayet stars also contribute to some of the most energetic events in the universe, gamma-ray bursts. When a Wolf-Rayet star collapses, its stripped envelope allows jets from the core to punch through more easily than in stars with thick hydrogen shells. If the conditions are right, high rotation, strong magnetic fields, the collapse funnels energy into beams of relativistic particles that flash as gamma-ray bursts across billions of light years. Thus, the enormous energy we see during their lives foreshadows even more extreme outbursts in their deaths, connecting stellar luminosity to cosmic catastrophe. Their energy output also plays a crucial role in galactic ecology. Wolf-Rayet stars inject energy into their host galaxies, heating interstellar gas and regulating star formation. Their winds clear out cavities in molecular clouds, dispersing the raw material for future generations of stars. At the same time, their ultraviolet radiation compresses nearby clouds, sometimes triggering star birth at their peripheries. In this way, they act as both destroyers and creators, disrupting old clouds while igniting new nurseries. The balance between suppression and stimulation depends on the environment, but the overall effect is clear. Wolf-Rayet stars are architects of their galaxies, sculpting the interstellar medium with their energy. Philosophically, their enormous output represents a paradox of excess. They are stars that give too much, pouring out energy at unsustainable rates, like lamps burning oil without restraint. Their brilliance is intoxicating but unstable. Their radiance magnificent but unsustainable. They remind us of the fleeting beauty of intensity, the truth that what burns brightest cannot burn forever. Their energy output is both their glory and their doom. From Earth, we see only faint points, often dimmed by dust. Yet behind those points lie powers that can remake regions of space. The light we collect in telescopes is not just illumination, but revelation, a glimpse of furnaces blazing with such ferocity that they sculpt the galaxy itself. They are small in number, but vast in influence, proving that a handful of extraordinary stars can dominate the dynamics of entire stellar neighborhoods. In the end, the enormous energy output of Wolf-Rayet stars is a story of extremes, of luminosity so intense it reshapes the cosmos, of winds so fierce they tear stars apart, of radiation so strong it reveals the very chemistry of galaxies. They are stars that burn too bright, their brilliance inseparable from their fragility. To study them is to confront the upper limits of what a star can be, to see energy not as gentle warmth, but as overwhelming force, a cosmic blaze that both dazzles and destroys. One of the most remarkable legacies of Wolf-Rayet stars is not simply their brightness or their ferocious winds, but their role as cosmic forges. These stripped stellar cores, blazing with immense energy, are sites where some of the universe's heaviest elements are created and dispersed. In their short and violent lives, Wolf-Rayet stars transform the simplest building blocks of the cosmos, hydrogen and helium, into carbon, nitrogen, oxygen, and beyond. Their instability ensures that these elements are not locked within them forever, but are hurled into the galaxy through winds and eventual supernovae, enriching the interstellar medium with the raw ingredients for planets, oceans, and life. Inside a Wolf-Rayet star, fusion proceeds at breakneck speed. With hydrogen largely stripped away, the core burns helium into carbon and oxygen, and then, in later stages, heavier elements form as fusion reactions pile layer upon layer of complexity. Unlike smaller stars whose outer envelopes conceal these processes, Wolf-Rayet stars expose their inner chemistry to the cosmos. Their spectra reveal broad emission lines, not of hydrogen, but of helium, carbon, nitrogen, and oxygen. A direct glimpse into the alchemy within. This exposure is what makes Wolf-Rayet stars so unusual. They are laboratories where we can watch the deep processes of stellar evolution on display. Astronomers classify Wolf-Rayet stars into subtypes based on which elements dominate their spectra. WN stars show lines of nitrogen and helium, indicating that the star is in a phase where helium fusion has brought nitrogen to the surface. WC stars, by contrast, display strong carbon and oxygen lines, a later stage when deeper fusion products are exposed. There are also rarer WO stars, which show oxygen at levels that suggest the star is near the end of its life, having stripped away nearly everything above its innermost layers. These spectral classes are more than labels. They are milestones in a star's journey from burning helium to its final collapse. Each stage reveals a chapter in the cosmic story of element production. The heavy elements produced in Wolf-Rayet stars are not just confined to their cores. Their stellar winds are strong enough to carry carbon, nitrogen, and oxygen out into space long before the final supernova. This makes Wolf-Rayet stars particularly important for galactic enrichment. They precede their surroundings with heavy elements, ensuring that when they finally explode, the region is already infused with the products of fusion. Nebulae illuminated by Wolf-Rayet stars often show these enriched elements glowing in emission, a visual reminder of how much material has already been ejected. These glowing shells are sometimes called Wolf-Rayet nebulae, and they stand as both memorials to the star's instability and as testaments to their generosity. This enrichment has profound consequences. Heavy elements are essential for forming planets, for creating atmospheres, and for enabling the complex chemistry of life. Without the carbon, oxygen, and nitrogen dispersed by Wolf-Rayet stars, rocky planets like Earth could not exist. Every breath we take, every carbon-based molecule in our bodies, every drop of water in our oceans is part of this story. The oxygen we breathe was once fused in the heart of a massive star, stripped away by winds or blasted out in a supernova. The carbon that forms the backbone of life's molecules was forged in stellar furnaces like these. Wolf-Rayet stars are therefore not only spectacular objects in their own right, but also ancestors of life, progenitors of the matter that makes us possible. The production of heavy elements in Wolf-Rayet stars also influences the broader evolution of galaxies. Regions with many such stars, like the cores of starburst galaxies, become chemically enriched much faster than quieter galactic neighborhoods. This enrichment changes the kinds of stars that can form in subsequent generations, influencing their masses, lifespans, and the dynamics of stellar populations. In this sense, Wolf-Rayet stars are architects of galactic futures, altering the composition of entire star-forming regions with the elements they disperse. Philosophically, this process reveals a profound cycle. The universe began with hydrogen and helium, elements formed in the Big Bang. Everything else, carbon, nitrogen, oxygen, iron, gold, was made later, in stars. Wolf-Rayet stars are central to this cycle, turning simplicity into complexity, lightness into weight, nothing into something. Their lives and deaths weave a tapestry of chemical abundance, out of which galaxies, planets, and life can emerge. They show us that the universe is not static, but creative, a place where matter itself evolves into new forms. There is also a sense of intimacy in this cosmic alchemy. When we look at the spectra of Wolf-Rayet stars and see the signatures of carbon and oxygen, we are looking at the very elements within ourselves. Our bones, our breath, our blood carry the imprint of stars that burn too brightly to last. Their winds scattered atoms across space, atoms that coalesced into the Earth and eventually into life. To reflect on this is to realize that the instability of distant, dying stars is written in our own biology. We are living memorials to their brilliance and their instability. Wolf-Rayet stars thus serve as reminders that death is not an end but a transformation. Their stripping, instability, and eventual explosions are not losses to the universe, but gifts, scattering matter into forms that will create worlds and living beings. Their heavy element production is the bridge between stellar physics and biology, between the death of giants and the birth of life. They embody the paradox of destruction as creation, of loss as renewal, of endings as beginnings. In the end, the heavy elements forged and released by Wolf-Rayet stars are among their greatest legacies. Their brilliance may fade, their cores may collapse, but the carbon, oxygen, and nitrogen they disperse will endure for billions of years, incorporated into planets, oceans, and organisms. To study them is not only to understand how stars live and die, but also to trace the origins of ourselves. The atoms of life are not accidents. They are the gifts of stars that burn too bright. The death of a Wolf-Rayet star is not only luminous and violent. In some cases, it may be the trigger for the most powerful explosions in the known universe. Gamma-ray bursts, GRBS. These extraordinary events unleash torrents of energy so intense that for a few seconds they can outshine every other source of light in the observable cosmos combined. The association between Wolf-Rayet stars and gamma-ray bursts is one of the most profound links in modern astrophysics, connecting the instability of stripped stellar cores to the most extreme transient phenomena we can observe. The reasoning behind this connection begins with the nature of Wolf-Rayet stars themselves. Their hydrogen envelopes are gone, peeled away by winds or companions, leaving bare helium and heavier layers above the core. When such a star undergoes core collapse at the end of its life, there is no thick outer layer to smother or choke the explosion. The lack of hydrogen makes it possible for jets of material to punch through the star and escape into space. In stars that retain their envelopes, these jets stall or dissipate. In Wolf-Rayet stars, they break free, forming the ultra-energetic beams of gamma rays that we detect as bursts. This theoretical framework is known as the collapsar model. In it, the collapsing core of a massive Wolf-Rayet star forms a rapidly spinning black hole or neutron star. Accretion disks funnel material onto the compact object, while magnetic fields and rotation launch twin jets at near light speed along the star's poles. As these jets punch through the stripped envelope, they collide with matter, producing shock waves and converting kinetic energy into gamma rays. For a few heartbeats of cosmic time, the star becomes a lighthouse blazing brighter than 1 trillion suns, beaming its death throes across billions of light years. Observations have confirmed this link. Many long-duration gamma-ray bursts, those lasting more than 2 seconds, are associated with Type 1b and IC supernovae, which are precisely the kinds of explosions expected from Wolf-Rayet progenitors. In 1998, GRB 980425 was found to coincide with supernova 1998 BW, one of the first direct associations of a GRB with a massive star collapse. Since then, dozens of similar connections have been made, reinforcing the picture that Wolf-Rayet stars are the likely culprits behind many of these cataclysmic bursts. Whenever astronomers detect a long gamma-ray burst in a distant galaxy, they suspect that somewhere within that galaxy, a Wolf-Rayet star has just met its end in spectacular fashion. The sheer energy of these events is difficult to imagine. In mere seconds, a GRB can release as much energy as our Sun will emit in its entire 10 billion year life. Yet because the emission is focused into narrow beams, the total energy may not be infinite, but is concentrated, like a cosmic blowtorch. If such a burst were aimed at Earth from within a few thousand light years, it could strip away our atmosphere and trigger mass extinctions. Fortunately, most Wolf-Rayet stars capable of producing GRBs lie in distant galaxies, far from us. Still, their power is a reminder of the dangers hidden in the universe, and of the role of hyperluminous stars in producing the most dangerous events we know. The connection between Wolf-Rayet stars and gamma-ray bursts also deepens our understanding of cosmic history. GRBs are so bright that they can be detected across nearly the entire observable universe, even from times when the first galaxies were forming. By studying these bursts, astronomers can probe the early universe, using the deaths of Wolf-Rayet stars as beacons to illuminate cosmic dawn. In this sense, Wolf-Rayet stars act as cosmic lighthouses twice over, once through their extreme luminosity in life, and again through their bursts in death. They shine not only as individuals, but as tools for exploring the furthest reaches of time and space. Philosophically, the association between Wolf-Rayet stars and gamma-ray bursts represents the ultimate expression of the paradox of brilliance and fragility. Wolf-Rayet stars burn too bright, shedding their envelopes and exposing their cores. And in doing so, they create the conditions for collapse into black holes and GRBS. Their very instability makes their deaths the most spectacular of all. What seems like weakness, the loss of their outer layers, becomes the channel through which their most violent power is unleashed. In their vulnerability lies their capacity for cosmic violence, a reminder that destruction often hides in exposure. Not every Wolf-Rayet star will end as a gamma-ray burst. The necessary conditions, rapid rotation, high mass, strong magnetic fields, and the right geometry, are rare. Many will collapse into ordinary supernovae or black holes without producing gamma rays. But enough meet the criteria that the connection is clear. Wolf-Rayet stars are the only class of progenitors that naturally explain the observed properties of long GRBs. Their stripped-down nature, their brevity, their instability, all conspire to make them the perfect candidates for the universe's most violent farewells. The study of this connection continues to evolve. Telescopes like Swift and Fermi monitor the skies for gamma-ray bursts, while follow-up observations with optical and infrared instruments hunt for supernova counterparts. Each new association strengthens the link between Wolf-Rayet stars and GRBS. Meanwhile, simulations of collapsing Wolf-Rayet stars refine our understanding of how jets form and break free. These studies bridge the gap between stellar physics and high-energy astrophysics, showing how processes within a single star can produce explosions visible across the cosmos. In the end, the connection to gamma-ray bursts makes Wolf-Rayet stars not only fascinating in their own right, but central to our understanding of the most extreme events in the universe. They are not just bright, unstable, short-lived stars. They are progenitors of cosmic lighthouses that can illuminate the universe from its earliest epochs. They are the link between the lives of stars and the vast, violent outbursts that allow us to study galaxies billions of light-years away. To contemplate Wolf-Rayet stars is to see not only the blaze of stellar brilliance, but also the most dramatic deaths the cosmos has to offer. Deaths that can be seen across the universe. Deaths that remind us of both the fragility and the fury of stars that burn too bright. Wolf-Rayet stars are paradoxes of abundance and scarcity. They blaze with such intensity that they dominate their local environments. Yet they are extraordinarily rare in number. In a galaxy of hundreds of billions of stars, only a few hundred Wolf-Rayet stars have been identified in the Milky Way. Their rarity is a natural consequence of their brevity. The Wolf-Rayet phase lasts less than 1 million years, a heartbeat in cosmic terms, compared to the multi-billion-year lives of smaller stars. To glimpse one is to catch a star in the midst of a fleeting transformation, exposed and unstable, destined for collapse. This rarity makes them all the more valuable as windows into stellar evolution. Because they represent a transitional phase in the lives of massive stars, each Wolf-Rayet star is a clue to how matter cycles through galaxies. Their stripped nature tells us how stars shed their envelopes. Their winds reveal the mechanisms of mass loss, and their spectra show us the chemistry of fusion at work. In their numbers, we see scarcity, but in their significance, we see abundance. They may be rare in count, but they are immense in influence. Wolf-Rayet stars also occupy a unique niche in galactic ecology. Galaxies are not static collections of stars, but living ecosystems, with stars being born, evolving, and dying in constant cycles. Wolf-Rayet stars are agents of disturbance in this ecosystem, injecting energy, matter, and momentum into their surroundings. Their stellar winds carve out cavities in interstellar clouds, blowing bubbles of hot gas that reshape the structure of the galaxy's medium. These winds are not trivial. They can carry away 10 or more solar masses over the course of the star's short life, sculpting the environment like hurricanes sweeping across a landscape. The effects of these winds extend far beyond the stars themselves. By clearing away gas in their neighborhoods, Wolf-Rayet stars can halt star formation locally, dispersing the raw material before it collapses into new stars. Yet at the same time, their winds compress the edges of surrounding clouds, triggering the collapse of material into new generations of stars. This dual role, suppressing in some places, stimulating in others, shows that Wolf-Rayet stars are both destroyers and creators. They regulate star formation, maintaining balance in the galactic ecosystem. Their eventual deaths amplify this role. When Wolf-Rayet stars explode as Type 1b or IC supernovae, they unleash shock waves that ripple outward, seeding space with heavy elements. The chemical enrichment they provide is one of their most significant ecological contributions. Without them, galaxies would remain poor in carbon, oxygen, and nitrogen, the essential ingredients for rocky planets, atmospheres, and life. Every grain of carbon in organic molecules, every atom of oxygen in water, owes something to stars like these. The elements of life are not accidents. They are the legacy of stars that burn too brightly to last. The rarity of Wolf-Rayet stars also means they often appear as jewels in stellar populations. They are disproportionately found in regions of intense star formation, such as spiral arms and starburst galaxies, where massive stars form in large numbers. Their presence is an indicator of youth. Because they live such short lives, any galaxy rich in Wolf-Rayet stars must also be forming stars actively. Astronomers use their spectral signatures as tracers of star formation rates, particularly in distant galaxies where individual stars cannot be resolved. In this way, Wolf-Rayet stars serve not only as participants in galactic ecology, but also as markers of galactic vitality. In binary systems, their role becomes even more dramatic. When paired with other massive stars, Wolf-Rayet stars produce colliding winds that generate X-rays, dust spirals, and even precursors to black hole mergers. Some of these binaries may ultimately collapse into double black holes, merging billions of years later and releasing gravitational waves, detectable across the universe. Thus, the rarity of Wolf-Rayet stars belies their outsized contribution to the tapestry of cosmic events. From galactic ecology to gravitational wave astronomy, their influence extends across domains of astrophysics. Philosophically, their rarity is part of their meaning. They are like fireworks, dazzling but brief, illuminating the sky only for a moment before fading. Their presence in the cosmos reminds us that not everything is common or enduring, that beauty is sometimes fleeting and precious. The fact that only a few hundred exist in our galaxy does not diminish their importance. It magnifies it, making each one a singular beacon of transience and power. Their rarity makes them symbols of impermanence, and yet their ecological role makes them symbols of continuity. For through their deaths, they ensure the survival of cycles larger than themselves. Their ecological role also reminds us that the universe thrives on disturbance. Life and renewal come not from stasis, but from turbulence, from stars that inject energy into their environments and force matter into new configurations. Wolf-Rayet stars are embodiments of this principle. Their instability and destruction are not flaws, but features, necessary parts of the cosmic machine that builds new stars, planets, and potentially life. To see their rarity is to see the exception. To see their role is to see necessity. Looking forward, the study of Wolf-Rayet stars continues to illuminate galactic ecology. With instruments like the James Webb Space Telescope, astronomers can now peer into dusty star-forming regions, where Wolf-Rayet stars sculpt their environments. Infrared imaging reveals the dust and molecules carried by their winds, while spectroscopy traces the chemical fingerprints of enrichment. Radio observatories like ALMA map the clouds they disturb, showing how energy input from a single star can reverberate across light years of space. These observations confirm what theory suggests, that Wolf-Rayet stars, though rare, are keystones in the architecture of galaxies. In the end, the rarity and ecological role of Wolf-Rayet stars capture their essence. They are few, but their influence is immense. They are fleeting, but their legacies are enduring. They are unstable, but their instability is fertile, scattering the elements of life and shaping the very fabric of galaxies. To contemplate them is to see the universe as an ecosystem, alive with cycles of creation and destruction, and to recognize that even the rarest stars can hold the greatest sway. Thorne-Zitkov objects, stars within stars. In the vast menagerie of cosmic objects, there are stars so exotic that they seem almost like myths. Thorne-Zitkov objects, TZOs, the so-called stars within stars. Proposed in the 1970s by physicist Kip Thorne and astronomer Anna Zitkov, these objects are hybrids, the unlikely union of two extreme stellar types, a massive red supergiant and a neutron star. If the theory is correct, then hidden within the bloated envelope of certain supergiants are collapsed remnants of dead stars, pulsing with unimaginable density and power. Such objects would be the cosmic equivalent of Matryoshka dolls, stellar Russian nesting dolls, with one star literally encased inside another. The concept arises from the violent dance of binary systems. Many stars are born in pairs or multiples, orbiting one another in gravitational partnership. When one of these stars is massive enough, it ends its life as a supernova, collapsing into a neutron star, an object so dense that a teaspoon of its matter weighs billions of tons. Its companion, if it survives, may continue its own evolution into a red supergiant, swelling to hundreds or thousands of times the sun's radius. If the orbital dance brings the neutron star too close, the smaller but denser object may plunge into the supergiant's bloated outer layers. Instead of passing through, it slows, spirals inward, and sinks into the core. The result is a red supergiant that contains a neutron star at its heart, a Thorne-Zitkov object. This scenario may seem improbable, but the physics is plausible. The dense neutron star, many times heavier than our sun, yet only a dozen kilometers across, would be like a bullet fired into cotton candy when it enters the extended atmosphere of a supergiant. Drag forces slow it down, and gravitational interactions cause it to spiral inward, losing orbital energy until it settles at the center. Once there, the neutron star effectively replaces the original core of the red supergiant. Instead of fusion occurring in the center, the supergiant's envelope is now supported by heat from exotic processes occurring on the neutron star's surface. The theory predicts some fascinating consequences. Normally, the core of a red supergiant burns helium, carbon, and heavier elements in concentric shells, generating the energy that puffs up its envelope. In a Thorne-Zitkov object, this central fusion engine is replaced by accretion, matter from the supergiant's envelope raining down onto the neutron star. As material falls inward, it strikes the neutron star's surface at near relativistic speeds, releasing prodigious amounts of energy. This accretion-driven heat stabilizes the star's envelope, keeping it swollen and luminous, even without a normal fusion core. From the outside, the star may look like a typical red supergiant, but internally it is something entirely different. A fusionless shell wrapped around a collapsed heart. Even more exotic is what happens at the boundary between the neutron star and the inflowing matter. Temperatures and pressures there would be extreme, far surpassing those in ordinary stellar interiors. Nuclear reactions not seen elsewhere in the universe could occur, creating unusual isotopes and heavy elements. The surface of the neutron star becomes a crucible for exotic burning, turning ordinary material into rare nuclei that might later be detectable in the star's spectrum. This is one of the key observational predictions of the Thorne-Zitkov model, that such objects should show anomalous chemical signatures, enriched in elements like lithium, rubidium, and molybdenum, in ways that ordinary stars cannot produce. The idea of a star within a star is both unsettling and captivating. It challenges our intuition about boundaries and categories. A neutron star, compact and dead, is normally thought of as the end of stellar life. A red supergiant, swollen and luminous, is thought of as a stage before death. A Thorne-Zitkov object fuses these categories, producing a hybrid that is neither fully alive nor fully dead, a star whose heart is a corpse, yet whose outer layers shine with borrowed vitality. It is a reminder that the cosmos often resists neat divisions, blending extremes into strange hybrids that stretch the imagination. The formation of a Thorne-Zitkov object would be rare, but not impossible. Binary interactions are common in massive stars, and collisions between remnants and companions are expected over cosmic timescales. Given the number of red supergiants and neutron stars in the galaxy, astronomers estimate that some number of Thorne-Zitkov objects should exist at any given time. They would not be numerous, but they would be out there, hidden among the countless glowing points of light, masquerading as ordinary supergiants. Philosophically, TZOs resonate with archetypes of hiddenness and disguise. Outwardly, they are ordinary, even mundane, red supergiants, like Betelgeuse or VY Canis Majoris. Inwardly, they harbor secrets, collapsed stars at their centers, dense beyond imagining. They embody the idea that appearances can deceive, that the most extraordinary realities can hide behind familiar facades. They remind us that the cosmos, like life itself, contains layers within layers, surprises within what we think we already understand. From a scientific perspective, the theory of Thorne-Zitkov objects is a test of how far our models of stellar evolution can stretch. It unites the physics of supernova remnants with the dynamics of binary interactions and the chemistry of nuclear burning. It suggests that stellar death is not always final, that remnants can find new roles within other stars, and that the cosmos is more inventive than we often assume. If confirmed, these objects would be a striking demonstration that even after collapse, a star can play a central role in the life of another. In the end, the theory of embedded neutron stars invites us to imagine stars not as isolated, self-contained entities, but as participants in a grander, more chaotic dance. Stars can collide, merge, and even consume one another. Out of these violent unions come hybrids like the Thorne-Zitkov object, stars within stars, living contradictions that testify to the creativity of cosmic evolution. They may be rare, but their very existence, even as a possibility, expands our vision of what a star can be. From the outside, a Thorne-Zitkov object would look deceptively ordinary. To a distant observer, it would appear as a red supergiant, a bloated star with a cool, ruddy surface, glowing faintly in shades of crimson. Its radius would be immense, perhaps hundreds or even 1,000 times that of the Sun, its outer layers so extended that their density would rival the vacuum of space itself. it would radiate with the same gentle warmth as other red supergiants. A beacon in the night sky that seems placid and majestic. Yet this outward appearance belies an interior of almost unimaginable strangeness. The familiar shell of the supergiant is not anchored by a conventional fusion core, but instead enfolds a neutron star. A collapsed stellar remnant only a few kilometers across, hidden like a diamond in a cloud. Red supergiants are among the most dramatic evolutionary phases of massive stars. Having exhausted the hydrogen in their cores, they expand outward, their surfaces cooling even as their luminosity remains enormous. Their envelopes are tenuous and unstable, supported more by pressure from below than by any intrinsic stability of their own. In an ordinary red supergiant, the shells surrounding the core are sites of nuclear burning. Hydrogen fusing into helium in outer shells, helium into carbon and oxygen deeper within, and eventually heavier fusion stages as the star nears collapse. These layers form an onion-like structure, with fusion shells stacked like strata, each one feeding the next until the core succumbs. In a Thorne-Zitkov object, however, the picture is different. Instead of a normal burning core, the envelope of the red supergiant wraps around a neutron star. The neutron star's intense gravity and accretion of material provide the energy needed to sustain the bloated shell. Matter from the inner regions of the envelope falls inward, accelerated to immense speeds, before slamming into the neutron star's surface. The resulting release of energy radiates outward, inflating the star and keeping it luminous. To the envelope, it hardly matters whether the heat comes from fusion or accretion. Energy is energy, and it is enough to hold the shell aloft. The red supergiant shell of a TZO is therefore both familiar and alien. It shares the size, luminosity, and cool surface temperatures of ordinary red supergiants, but its source of support is fundamentally different. Without fusion in the core, the internal dynamics of the envelope shift. Instead of being layered with predictable burning shells, it becomes a convective cauldron, churning with turbulence as energy is transported outward. The envelope of a TZO may be even more unstable than that of a normal red supergiant, prone to pulsations, irregularities, and eruptions. These instabilities could cause the star to vary in brightness, flickering subtly in ways that might betray its exotic heart. One of the most fascinating consequences of this structure is the chemical mixing that occurs in the convective envelope. Material processed near the neutron star's surface, where exotic nuclear reactions may take place, can be dredged upward and carried into the outer layers. Unlike in normal stars, where heavy elements are often confined to inner shells until the final explosion, in a TZO, those elements can reach the surface while the star is still alive. This means the red supergiant shell of a TZO might be enriched with unusual isotopes detectable in its spectrum. Lithium, rubidium, molybdenum, and other anomalous elements could appear in abundance, serving as telltale fingerprints of the strange physics within. Thus, the apparently ordinary face of the red supergiant may carry subtle clues that it hides a neutron star within. The sheer size of the red supergiant shell also plays a role in concealing the neutron star. Imagine a core the size of a city buried beneath an envelope that could engulf Earth's orbit many times over. Light and energy from the central neutron star must diffuse through this enormous expanse before reaching the surface, smoothing out any obvious signs of its presence. From our vantage point across light years of space, the difference between a normal red supergiant and a Thorne-Zitkov object may be nearly invisible. It is only in the fine details of the spectrum, the anomalies in chemical abundances, that the disguise might slip. Philosophically, this image of a neutron star hidden inside a red supergiant shell is rich with metaphor. It is the ultimate contrast, a heart of unimaginable density and violence cloaked in a shroud of softness and cool light. The shell is an illusion of calm, a mask that hides the truth within. It suggests that what appears gentle and ordinary may conceal extraordinary extremes. It reminds us that the universe is layered, that what we see on the surface often tells only a fraction of the story. The red supergiant shell also raises questions about longevity. How stable can such a configuration be? The envelope is constantly feeding mass to the neutron star, which radiates energy back outward. Over time, this process may alter both the neutron star and the shell, eventually destabilizing the entire object. Some models suggest that TZOs may be relatively short-lived, lasting only tens or hundreds of thousands of years before collapsing or shedding their shells. If so, then part of their rarity stems not only from their unusual formation, but also from their fragility. They are fleeting hybrids, stars that hide their true selves only briefly before revealing their strangeness in collapse. From the standpoint of galactic ecology, the red supergiant shell of a Thorne-Zitkov object is more than camouflage. It is also a dispersal system. Winds and pulsations carry away material enriched by unusual nuclear reactions near the neutron star's surface. These enriched outflows seed the galaxy with elements not typically found in such abundance, adding to the chemical diversity of the interstellar medium. In this way, even the cloaked existence of a TZO contributes to the long-term evolution of galaxies, ensuring that its hidden processes have visible consequences. In the end, the red supergiant shell of a Thorne-Zitkov object is both ordinary and extraordinary. It looks like any other massive dying star, yet it conceals a heart unlike any other. Its disguise is so convincing that only the most careful observations might reveal the truth. To contemplate it is to see how the universe can hide wonders in plain sight, how the most extraordinary phenomena may masquerade as the familiar. The shell is a mask, the neutron, star, a secret. Together, they create one of the strangest and most beautiful possibilities in all of astrophysics. A star within a star. If the defining feature of a Thorne-Zitkov object, TZO, is a neutron star hidden inside the bloated body of a red supergiant, then the true strangeness of these objects lies in the energy signatures and exotic reactions that result from such an improbable configuration. Where ordinary stars draw their stability from fusion in their cores, a TZO must balance its enormous envelope on a very different kind of engine. Accretion onto a neutron star, and the extreme nuclear processes that occur in its presence. This unique arrangement produces signatures unlike any other star in the cosmos. Strange chemical enrichments, unusual luminosity patterns, and a form of nuclear alchemy that seems almost otherworldly. At the center of a TZO, the neutron star acts as an anchor. Matter from the surrounding red supergiant envelope continuously falls inward, pulled by the neutron star's immense gravity. As it accelerates, it reaches near-relativistic speeds before crashing onto the neutron star's surface. The kinetic energy of this infalling matter is converted into heat, releasing vast amounts of energy. This process of accretion heating is capable of producing luminosities comparable to or even exceeding those of fusion-powered stars. Thus, while a TZO might look like a normal red supergiant from the outside, the source of its energy is profoundly different, a collapsed stellar remnant, devouring its host from within. The environment at the boundary between the neutron star and the infalling gas is extreme beyond anything we can reproduce on Earth. Densities soar, and temperatures climb into the billions of degrees. Under such conditions, nuclear reactions that would be impossible in ordinary stellar interiors suddenly become viable. These include processes known as the rapid proton process and the hot CNO cycle, exotic chains of nuclear fusion that generate unusual isotopes and rare heavy elements. Unlike the stable fusion burning in main sequence stars, these reactions occur in turbulent bursts, driven by the constant rain of matter onto the neutron star's surface. The result is a chemical laboratory unlike any other in the universe. One of the most important predictions of Thorne and Zitkov's model was that these exotic reactions should leave observable fingerprints in the spectra of TZOs. In particular, they suggested that such stars would produce excess amounts of certain elements that are not normally abundant in red supergiants. These include lithium, rubidium, molybdenum, and other S-process and R-process isotopes. Because the convective envelope of a red supergiant is so turbulent, these products would be dredged up to the surface and eventually ejected into space through stellar winds. Thus, if astronomers were to detect anomalous abundances of these elements in a supergiant star, it could be a telltale sign that a neutron star lurks within. This makes the energy signature of a TZO fundamentally chemical as well as thermal. Unlike a normal supergiant, which reveals a familiar pattern of hydrogen, helium, and heavier elements in expected proportions, a TZO would appear chemically peculiar, enriched in ways that defy standard stellar evolution. The presence of strong lithium lines, for example, would be unusual, since lithium is normally destroyed in stellar interiors rather than created. Its unexpected appearance in a supergiant spectrum could be evidence of the exotic alchemy occurring in a TZO's heart. Similarly, molybdenum and rubidium, elements rarely produced in significant quantities by ordinary stars, would stand out as markers of this hidden physics. Beyond chemistry, TZOs may also display unusual luminosity profiles. Because their energy is derived partly from accretion rather than fusion, their brightness might vary in ways not typical of ordinary red supergiants. They could flicker or fluctuate irregularly, depending on the rate at which matter falls onto the neutron star. Such variability would be subtle and difficult to distinguish from the natural pulsations of red supergiants, but in principle, it could provide another clue. A star whose light seems oddly unstable, or whose energy output does not match its spectral type, could be hiding a neutron star at its core. The exotic nuclear reactions inside a TZO also carry profound implications for galactic ecology. By creating unusual isotopes and ejecting them through winds, these objects could enrich their surroundings with elements that are otherwise rare. While their contribution to overall galactic chemistry would be small due to their rarity, the specific fingerprints of their nucleosynthesis could shape certain environments in distinctive ways. If confirmed, TZOs would stand as one of the universe's rarest and most creative forges, crafting elements through mechanisms unlike any other. Philosophically, the existence of such energy signatures is compelling, because it challenges our definitions of life and death in stars. A neutron star is normally a dead remnant, its fusion finished, its energy only the ghostly release of cooling or magnetism. But inside a TZO, that same remnant becomes the catalyst for new nuclear processes, feeding on the envelope around it and igniting reactions impossible elsewhere. It is as if death itself becomes fertile, the corpse of a star generating new creation within the body of another. The TZO is therefore a paradoxical creature, a symbol of transformation where endings and beginnings merge into one. The challenge for astronomers is that these energy signatures are subtle. A TZO looks at first glance like any other red supergiant, large, cool, and luminous. Its chemical peculiarities can only be discerned through detailed, spectral analysis, and even then they may be masked by the complexities of turbulent stellar atmospheres. Detecting one requires patience, precision, and often a bit of luck. This difficulty explains why Despite decades of searching, only a handful of candidates have ever been proposed. The universe may be hiding these hybrid stars in plain sight, their energy signatures faint whispers against the roar of stellar evolution. In the end, the exotic reactions and energy signatures of Thorne-Zitkov objects are the best evidence we might ever have of their existence. They are the fingerprints of impossibility, clues that point to a star unlike any other. To contemplate them is to imagine a universe where even the strangest ideas can take shape, where the death of one star can nest within the life of another, and where energy is released not by ordinary fusion, but by the intimate dance of collapse and survival. These energy signatures are the ghostly voices of stars within stars, whispering that the cosmos is stranger than we dare to dream. For decades after Kip Thorne and Anna Zitkov proposed the existence of stars within stars, these strange hybrids remained purely theoretical. The mathematics worked. The physics seemed plausible. But without observational evidence, Thorne-Zitkov objects, TZOs, remained speculative curiosities, whispered of in conference halls and textbooks, but not geysers. From the outside, a TZO looks almost exactly like an ordinary red supergiant, of which there are thousands scattered throughout the Milky Way and nearby galaxies. Only in subtle details: chemical anomalies, unusual variability, strange emission lines. Could their exotic natures be betrayed? Finding one would be like searching for a single unusual stone on a beach, littered with millions of others. The difference is visible only under careful inspection. The first real breakthrough came in the 2000s, when astronomers identified HV 2112, a star in the Small Magellanic Cloud, as a possible candidate. Spectroscopic studies revealed unusual abundances of elements such as lithium, rubidium, and molybdenum, precisely the kinds of signatures predicted for a TZO. These anomalies stood out against the background of normal red supergiant chemistry, suggesting that something exotic might be happening in HV 2112's interior. If it truly was a TZO, it would be the first observational confirmation of Thorne and Zitkov's half-century-old hypothesis, a discovery that would immediately reshape our understanding of stellar evolution. Yet the story was not so simple. HV 2112's status remains controversial. Some studies argue that the star's peculiar chemistry could be explained by other processes, such as asymptotic giant branch, AGB evolution, or unusual mixing events in supergiants. Others suggest that the star's position in the sky complicates its classification, with uncertainties about whether it truly belongs to the Small Magellanic Cloud, or is instead a foreground object in the Milky Way. The ambiguity highlights the central difficulty of TZO research. The very signatures that might reveal them are subtle enough to be explained away by alternative models. A single spectrum is rarely enough to settle the question. Multiple lines of evidence are needed to distinguish a TZO from other exotic but more conventional stars. Other candidates have since been proposed. In the Milky Way, a handful of red supergiants in clusters like Westerlund 1 and 2 have shown unusual chemical fingerprints that sparked speculation. Some exhibit enhanced lithium or rubidium, elements not typically found in abundance at their surfaces. These findings hint that they may harbor neutron star cores, though confirmation remains elusive. The rarity of both red supergiants and neutron stars aligning in just the right conditions makes TZOs inherently rare, and their short expected lifetimes mean that we may only ever see a handful at any given moment in a galaxy as large as our own. Another avenue of observation comes from studying the variability of candidate stars. Because the energy source of a TZO is accretion rather than fusion, their luminosity may fluctuate in unusual ways. Some candidates show irregular light curves, with brightness waxing and waning unpredictably. These fluctuations may reflect instabilities in the accretion process, as matter rains down on the neutron star at varying rates. Yet, variability alone is not conclusive evidence. Many red supergiants are naturally unstable and variable. Thus, variability must be combined with chemical anomalies to build a stronger case. The search for TZOs has also extended to other galaxies, where massive populations of red supergiants reside. In nearby galaxies like the Large Magellanic Cloud and Andromeda, astronomers comb through catalogues of luminous red stars, looking for the telltale spectral fingerprints of exotic nucleosynthesis. HV 2112 remains the best-known extragalactic candidate, but surveys continue to refine the sample, searching for new anomalies that could reveal hidden neutron cores. If TZOs exist, then at least a few should be hiding among the countless luminous points in these galaxies. The challenge is not their absence, but our ability to discern them amid the noise of stellar diversity.